Okay, good morning. Thank you all for being here. So the reason we're here at SIGGRAPH today is to talk about how deep knowledge from the graphics community on things like Monte Carlo rendering and spatial data structures can be used not just for light transport, but for much broader physical problems. So things like thermal diffusion or electrostatics or even fluid mechanics on complex three-dimensional domains. And we hope that not only will we stand up here and present a lot of information to you, but that we'll also learn a lot from you all in discussions today and throughout the rest of the week, because this is an area where there are really some big open questions that we've been banging our head against. And really, truly, the people in the computer graphics community are uniquely poised to solve a lot of these long-standing problems. So kind of on that note, the organizers for this conference and the presenters are all from computer graphics. So Rohan, Sawhney, Bailey Miller, Ioannis, Gkioulekas, and myself, Keenan. And we have a great list of invited speakers: Wojtek Jaros, Shuang Zhao, Sina Namizadeh, and Zilu Li. If you know some of the people on this list, you might be thinking, okay, well, why do you have a bunch of researchers with backgrounds primarily in rendering and light transport if you want to give a course on simulation and differential equations? And the basic reason is, well, Monte Carlo rendering has a lot of features that we really, really wish we had in the simulation setting. So for instance, Monte Carlo rendering handles arbitrary geometric complexity without performing any kind of simplification or model reduction. So here we have a real-time demo of Monte Carlo rendering with vastly complex geometry, this one coming from NVIDIA. It also provides instantaneous feedback and sort of progressive previews of what you're working on, which is really helpful in any kind of design cycle. So if I can get that kind of immediate feedback, I don't have to wait a long, long time to make little tweaks to my design and see if those parameters are good. And of course, this is also tied into sort of differentiable optimization of different engineering problems. Perhaps most importantly, in terms of building a larger system, Monte Carlo rendering really just works no matter what you throw at it, meaning it produces a reasonable answer with essentially no preconditions on the geometry. So here, for instance, even if I totally mess up all the polygons in the mesh, I still produce a really beautiful image. The solver doesn't crash out on me like it might with a finite element solver. So from a systems and computational point of view, we can do a totally awesome job of simulating light transport. However, there's, of course, a lot more to the physical world than just light. For instance, we might need to understand heating and cooling, or whether a building will stand up, or how an electrical device might work, and so on. And so our goal here today is to think about a much broader scientific and engineering context outside of just image generation. For instance, as just one example, here's an image of NASA's Curiosity Mars rover. Actually, many of you may quickly realize this is not a photograph, because who would be taking it, but rather it's a rendering of the rover. And in fact, it's not a rendering of an official engineering schematic from NASA, but rather just some low-quality amateur model that we downloaded off the web. Okay? And yet it looks really, really good, right? And this is kind of the state of the art in rendering. It just works. You can make some pretty compelling images, get quick feedback, no matter what kind of crazy model you throw at it. But that's probably not what you need to do at NASA, right? What if you need to predict something other than just appearance? For instance, NASA's own guidelines tell engineers that thermal modeling is required beginning at the project conceptual design stage and continuing through preliminary and detailed design stages. Simplified calculations and rules of thumb are useful, but a computer model provides the ability to evaluate and respond quickly to proposed system trade-offs, okay? So NASA is telling its engineers, hey, you should be checking your design at every moment against simulation. And that's a really nice dream. It'd be great if you could do that, except, well, simulation is not like rendering, right? Even if I have defects on just some small part of my mesh, the solver might just totally give up. Or worse, it might not give up and give you some kind of physically ridiculous result without actually knowing, without actually warning you that, hey, this solution is non-physical. And that's a real danger if you're sending things into space, okay? So to ground our discussion a little bit and to sort of set the stage for today, I want to talk specifically about problems where you have simple physics and complex geometry. Light transport is already one of these, right? The differential equation it solves, the light transport equation, is very simple. It's linear and first order. But the geometry can be extraordinarily complex. Moving beyond light transport, we might think about something like thermal analysis for, let's say, a data center. Again, the thermal equations are not that complicated, but the geometry of the data center and all the machines and the corridors and the insulation and everything going on is extraordinarily complex. Likewise, I might be doing analysis of a vastly large circuit, right? I'm doing integrated circuit design, and I have to solve relatively simple electrostatic equations that describe things like voltage or capacitance, right? So there are a lot of these scenarios where you have extremely complex geometry and relatively simple physics. Mathematically, many of these quantities can be modeled using partial differential equations, or PDEs. Our model equation, which we'll talk a lot about in this course, is the Laplace equation, which describes sort of a geometric interpolation problem. So for instance, suppose I have some object and I can observe the temperature only on the boundary, only on the outside. And what I'd like to do is predict or guess what's going on inside. I want to know the temperature deep inside the solid object. So the answer to this problem, at least for a fairly simple physical model, is given by the Laplace equation. Delta U equals 0 on the interior and U equals G on the boundary. So it has some kind of smoothness on the interior and it agrees with our observations on the boundary. The common belief about problems like the Laplace equation is that if you want to solve it on a computer, you must use some kind of finite dimensional approximation. And this is basically how all traditional methods work: finite elements, finite differences, you name it. For instance, you might build a mesh of your domain so that you can define basis functions and then ask your equation to hold in a weak sense. So integrating the proposed solution against any basis function should equal the right-hand side. If you do this, of course, you're going to have errors. You're going to have errors due to approximation of the geometry, and you're also going to have errors due to approximation of the underlying function space. Okay, and this is something that we, in simulation, have all just kind of accepted as, that's just the name of the game. There's nothing you can do about it. Actually, it turns out that you can avoid finite dimensional approximation completely by using Monte Carlo methods to solve these kinds of problems. Okay, and I'm not going to tell you exactly how this works right now. That's the point of the course. But basically, we're going to develop something called the walk-on-spheres algorithm that's a lot like recursive ray tracing. So it's sort of a ray tracer for physics. And so the sort of very high-level description is I take a bunch of random walks through the domain, repeat those random walks a large number of times, and take an average, right? Just as in Monte Carlo rendering. Okay? The sort of interesting thing about this is, similar to rendering, where the basic operation is computing ray geometry intersections, the only geometric operation we need are simple closest point queries. Given a point in space, what is the closest point on my domain boundary, or my boundary representation? Okay? So, okay, that's a cool story. Maybe that's mathematically interesting or something. But why do we want to solve it this way? How does this actually solve any of our problems? Well, here's the answer. Even very, very smart people at Pixar are saying, I hate meshes. I cannot believe how hard this is. Geometry is hard. And I think if you've ever had to work with meshes in your life, you might have experienced some pain. In contrast to meshing, doing volumetric meshing of a domain, finding the closest point on the boundary of a domain is a very, very simple operation that scales well, right? That can be parallelized, all these kind of things. And this is very important because geometry is only getting more and more complex as the years go on. We have extremely detailed data coming from laser scanning and shape optimization and computer vision and all sorts of other places. And even after decades of working on methods for solving PDEs, we still struggle to handle the level of geometric complexity that we see in nature. Nature is still beating us. Nature is still, way more complex than even our most impressive finite element solvers, finite difference solvers, and so on. Okay. And even state-of-the-art tools for solving these problems can take hours even for a single model, right? So here's a fairly interesting model, several million polygons, and it takes 14 hours and 30 gigs of RAM to generate a simulation quality mesh using state-of-the-art tools published here at SIGGRAPH just a few years ago. Okay? So forget about doing any kind of iterative design or differentiable optimization if you're waiting for the thing just to mesh. Okay? So that's kind of the point. If we spend all of our time cleaning up our mesh, converting it into a volumetric, tessellation, and so on, who cares how much faster you make your simulator? You made your finite element simulator 10 times faster? Great. You're still waiting for the mesh to be created. Now, one approach is just to keep pushing on better and better meshing tools. And to be fair, these have gotten extremely good. People have done some really beautiful stuff, especially in recent years, on making meshing robust and work in all sorts of scenarios. But every time you actually go to use one of these tools, you feel like, meshing feels like a problem that's never really going to be completely solved. I can always throw some mesh at it where something goes haywire. So here's an example of just even very, very simple geometry. This is a small piece of a watch, okay? And again, the same state-of-the-art mesher takes hours to mesh this, not because the geometry is complicated, but because it gets tripped up by the description of the boundary, okay? And that's, again, a real problem in practice. The other issue is that even when it succeeds by some sort of academic metric, like, oh, I can guarantee my algorithm terminates, it might not produce something that really solves the engineering problem or the physical problem. So you can end up with situations where critical details can be lost. Here, for instance, in this anatomical model, yeah, we get a valid tetrahedral mesh, but we do that at the cost of simplifying away pretty important geometry like veins that run through the body, okay? And so what this kind of tells us is to faithfully simulate nature, we really must be able to handle a much greater level of geometric complexity than we're dealing with today. So back in the 1990s, people in rendering ran up against the same kind of limitations. So back then, if you wanted to make a photorealistic image, you might use something called finite element radiosity, where, like we've been talking about, you make a mesh of the scene. Okay, so you really dice up all the geometry, including, you'll see here in this picture, you cut up the geometry even along things like shadow boundaries, right? This was really, really kind of a nuts way to do illumination calculation relative to how we do it today. Okay, so you have to mesh the scene, build this giant global system, and then solve it. And this idea fell out of fashion for a number of reasons, but in large part because meshing, again, is just really, really hard. And instead, what happened is the rendering community moved away from finite element methods and toward Monte Carlo methods, where you just recursively shoot rays that bounce around the scene and sort of collect information about illumination. And so now, instead of meshing, again, you just have to compute this very, very simple geometric query. Where does a ray pierce the geometry? Which is much easier to do. In fact, about 25 years ago, right here at SIGGRAPH, there was another course on Monte Carlo rendering advocating for the same point of view. Like, hey, maybe we should move away from meshing and finite elements, and maybe we should just replace it outright with Monte Carlo methods. And many of you know what's happened in the 25 years since. Right? Monte Carlo rendering has really revolutionized a huge number of different areas and industries, and not just entertainment, but architectural visualization, and now into sort of inverse problems in computer vision and machine learning and robotics. Right? Because it has that robustness, because you can build it into a system and know that it's going to work. It's not just, you're just working on this one meshing product, but it's just a component that works somewhere inside a bigger system, okay? And so today, we want you to come take a walk with us, right? Come take the next part of that journey, moving from doing recursive ray tracing to simulate just light transport, to doing recursive random walks that can simulate a broader set of physical phenomena. The payoff is going to be that simulation is going to behave a lot more like rendering. For instance, if we go back to our example of the Curiosity rover and NASA engineers trying to adjust their model to match some thermal properties, it now becomes possible to get immediate progressive feedback. Right? So we instantly get a few samples that tell us about what's going on. Just like Monte Carlo rendering, we can also focus our computational effort only where we really need it as humans looking at the output. Right? Rather than solving some big global volumetric finite element solve and then only looking at the one part we're interested in, why don't we spend that computational budget looking at the thing that we're trying to design or improve? And the greatest thing is we can avoid this nightmare of mesh generation and waiting hours or running out of memory in trying to even put our simulation domain into the solver in the first place. Okay, now, without all that propaganda out of the way, I have to say, I'll be candid. The solvers today we're going to discuss today are not a silver bullet for solving all problems in simulation. Okay? As I said, we're going to focus on very, very complex geometry, but relatively simple physics. Okay? And I fully acknowledge that there may be some simulation problems that we can never solve using this Monte Carlo walk-on spheres approach. It's very, very good that we have this whole ocean of other simulation methods, for the rich variety of problems that we see in the world. But given how far Monte Carlo methods have brought us in understanding and simulating and predicting illumination, we would be crazy to say, oh, it can only solve the Laplace equation, so we should give up on it, right? Because think about it, in rendering, for instance, again, even outside of entertainment, people really use Monte Carlo rendering when they design buildings to say, how is the illumination going to look before I build this thing? It would be just enormously expensive and painful if it wasn't until I built the building and put the lights in the room and I said, oh, I really should have designed the walls differently. Right? So imagine we can do that same kind of thing for analyzing, even at a basic level, the heating and cooling in a building before we build it. Right? I want to minimize energy costs, something that's very relevant to our world today. And I'd like to be able to explore the space of design possibilities from an extremely complicated geometric model before ever putting my shovel into the ground. Okay? So very, very much worth exploring this sort of emerging area and what it can do. Okay, so what are we going to do today? Part one is just going to be basics of Monte Carlo and looking at a walk-on spheres estimator for this, this first problem, this Laplace problem with Ioannis. Part two, Bailey is going to walk us through the walk-on spheres for a slightly more interesting PDE, the Poisson equation with Neumann boundary conditions. I'm going to step in at a couple points and show how to actually do this in code, so there'll be a nice mix of theory and practice throughout the course. Part three, Rohan's going to talk a little bit about an important sort of complementary perspective of walk-on spheres as Brownian motion, as sort of a stochastic point of view, rather than this integral point of view. We'll take a break for 5 minutes. During that break, by the way, we're going to stay here and answer questions. So if you have nowhere to go and you have a burning question, please step up to the stage or step up to the microphone and ask. In part four, we're going to bring in our guest speakers who are going to talk about some more advanced topics, some of the sort of cutting edge stuff that's going on right now, techniques for variance reduction, making things faster, differentiable solvers for inverse problems, so sort of automatically figuring out model parameters, handling exterior problems, so I care about not the inside of the object, but what's going on everywhere else, and finally, talking about hybrid neural and Monte Carlo solvers, so working sort of learning-based ideas into the picture. And at the very end, we'll talk about some applications, limitations, and open problems. As I said, we have a huge, huge set of things that the 4 of us or the 8 of us just don't have the resources or the brain power to solve, and we would love to talk to all of you about how to crack some of these hard problems. Okay, and then we'll have a Q&A at the very end. All right, and that's it. So I'll bring up Ioannis Gkioulekas, who will give us the first part of the tutorial.
All right. Hello, everyone. Thank you for being here with us this morning. My name is Ioannis Gkioulekas, and I'm going to start by talking about basics of Monte Carlo. So we are coming here with a rendering background. The things I'm going to present will be very familiar to you. Even if you are not, if your background is not in rendering, you may still have seen a lot of the stuff that I will cover in graduate courses or your undergrad courses on numerical integration and numerical computing. But I hope that by overviewing exactly how Monte Carlo works, in particular how it works in the case of integration, I'm going to make it concrete for you why we care to create Monte Carlo methods for simulation. All right? A lot of these notes come from a course that Keenan and Gautam here at CMU have put together on Monte Carlo methods for integration, so thanks a lot for that. So Monte Carlo methods are one of many types of randomized algorithms where we have to use repeated random sampling, repeated experiments to try to form a numerical estimate of some unknown quantity, to be able to approximate the solution to some computational problem. And this problem can take various forms. It can be integration, it can be optimization, it can be sampling. Integration will be the focus we have here, but that's just one of the types of problems we can solve using Monte Carlo. And importantly, not all randomized algorithms are Monte Carlo algorithms. For example, we have algorithms such as Las Vegas algorithms, where we use multiple random experiments and random sampling experiments to try to find the exact solution of some problem. Here, we're not going to aim for exact solution. We're going to aim for an approximate numerical solution using Monte Carlo. And to give you just a quick idea of how Monte Carlo works, and also to highlight some of the nice features they have in a hopefully intuitive way, I'll look at a very simple toy problem where we are looking to, we have cookies of different size, and we're trying to compute the size of those that we can assign a price to them, or maybe you're getting worried about your sugar intake and you're trying to figure out which cookie is safer to, or better to eat than another. Now, the problem is that to do any of these would be, we want to figure out the area of each one of these arbitrarily shaped cookies. And computing the area becomes harder and harder the more complex the shape of the cookies. In some cases, we may be able to do this analytically, but as the shape becomes more and more complex, analytical solutions will quickly become impossible, okay? So you can try to use Monte Carlo, or some flavor of a Monte Carlo experiment, to approximate this area. And here is how this works. We take our cookie, we place it inside some other simpler shape for which we know the area, and we start picking points randomly inside that, for example, by throwing darts. And for each dart, we go and check, did it hit the cookie or did it hit the other shape? Did it miss it? So then if I take the ratio of how many of the darts are through hit the cookie versus the total number of darts, and also multiply by the area of the plate on the plate where I place the cookie, I will end up with an estimate of my cookie area, a Monte Carlo estimate of my cookie area. Now this and this is an area procedure I can use to estimate the area of any arbitrarily complex shape I use for my cookie or for any other kind of shape for which I'm looking to estimate the area. Now this toy example already gives me already shows some of the features why Monte Carlo algorithms are nice. For example, the algorithm is very simple. I don't need to worry about subdividing the shape into other simpler shapes that I know analytically. All I need to be able to do in this case is pick points, throw darts, and also importantly figure out whether they hit the cookie or not. Second, the solution is approximate, but as we see in this plot, it converges close to the correct estimate quite fast. So after a few trials, after a few random darts, I will be able to figure out what the area of the cookie is. And it's also very easy to parallelize. I can start throwing darts in parallel, or I can repeat this experiment with multiple cookies and average the results, and arrive at an accurate estimate of the solution faster. Okay? Now, what we will be focusing on is not computing areas of cookies, but rather solving problems involving integration, which are actually pretty common in computer graphics and in general in scientific computing. Within graphics alone, we have light transfer problems, a lot of PD simulation problems, as we'll see, maximum likelihood estimation, that's basically all of empirical minimization in machine learning, and so on. And our general recipe will be to first write down the problem in some concrete mathematical terms. In the case of PD simulation, that's to set up the PD and the boundary conditions we care about. Then to convert that into an integral. And then lastly, to apply Monte Carlo estimation to evaluate that integral and see what algorithm this takes us on. And as I mentioned, our focus will be primarily on partial differential equations, and the resulting Monte Carlo estimate will be the walk-on-spheres algorithm, and later, as Bailey will present, the walk-on-stars algorithm, and also some new algorithms that our invited speakers are going to cover. Now, let's see how Monte Carlo works specifically for integration problems. And if you're getting worried that you don't remember exactly your rules of integration, don't really worry about that, because what we're going to be focusing is integrals for which we cannot analytically compute the integration value. And these are actually most of the integrals that we run into in real life and in the real scientific problems. In fact, even if you look at some very simple problems, like the integral of the sinc function over here, or the length of an ellipse, these are all problems that surprisingly don't have an analytical solution. So we're going to have to approximate them numerically one way or another. Now, probably the best known and simplest numerical approximation procedure for an integral is to use numerical quadrature. It's really the way that you are usually introduced to integrals in high school, and it's the main numerical approximation procedure we learn as undergrads or graduate students throughout our numerical computing education. And what it says is that I'm going to take my integration domain, and I'm going to break it up into deterministic discrete intervals. Generally, often, not generally, of the same size. I can also start varying the size of the intervals I use. Importantly, all of those I know them in advance. They're deterministic. And then, within each one of those intervals, I use some rule, like the midpoint rule, to approximate the value of the function as if it were constant in this integral. I sum up all of these values, I weight them by the size of each of the interval, and that gives me an estimate of the integral value. And that generally works pretty well. So what's the catch here? Like, why do we not want to do that and would rather use Monte Carlo? The problem is that if I start looking at integrals beyond one dimension, I run into the curse of dimensionality. In particular, if I have to compute an integral not in one dimension, as in the toy example before, but in 2, in 3, in 4, in 5, and so on, I need to now start using not discrete intervals, but higher order voxel, which means that the amount of effort I have to do, the amount of compute and the amount of memory I need to store increases exponentially with dimension. So the higher the dimension of the problem, the more expensive, and again, exponentially more expensive it is to be able to do quadrature. And then I also have the problem that quadrature techniques, deterministic discretization techniques, are inherently affected by aliasing. If I have a smooth function such as the one over here, discretizing and using quadrature is going to work very well. But the same discretization will not work for a function that's much more highly oscillatory, or will not work for a function that has spikes, potentially strong discontinuities, and so on. Now, for the middle case, for the oscillatory function, the Nyquist-Shannon theorem tells me that there is some point beyond which I can set the sampling frequency I have so that I can get an accurate value. So that function is not hopeless. It's just going to become more expensive to be able to estimate it with numerical quadrature. But there are functions for which the highest frequency can be infinite. So if I have discontinuities, if I have multiple frequencies at all, continue increasing, in all of these cases, there's not going to be any discretization frequency that's going to give me the correct value. Okay? So I have a curse of dimensionality problem, and I have an aliasing problem. And all of these issues are issues that actually show up in real-world situations, where my integrals tend to be very high-dimensional, and also where the function I'm looking to integrate can have all of the problems I just mentioned in aliasing. If I look at this photo over here, I can see that it has discontinuities, where I have the visibility change, the foreground change to background. I have high-frequency patterns, like the texture that's formed at the back by the skyline and the buildings, and I also have spikes, like in this case, the bright patterns that the cars create on the bridge. And yet, in areas in graphics, such as rendering, we are able to deal with all of these issues by simulating light transport as an integration problem without running into any of the pitfalls that quadrature has. So how do we do that? We do that using Monte Carlo. All right? So I'm going to switch gears. I'm going to start now talking about how to solve the same kind of integration problem, not with quadrature, but with Monte Carlo, and how exactly this helps us address all of these problems. So what do we do in Monte Carlo? We have, again, the same function. And again, we're going to sum estimates of this function at specific points, at specific samples along the domain of integration. Except that now, instead of placing those deterministically, we're going to place all of those points randomly. How do I select these points? The simplest thing I can do, and one that's generally pretty effective if I don't have a better solution, is to simply sample these points uniformly. I just go in this line, and I uniformly pick the points where I'm going to do the evaluation. Then within these points, I evaluate my function, I average the evaluations I have, and I also multiply by the total size of my domain. So this is another estimate of my integral that, again, will end up being, as we'll see in a few slides, correct in the sense that it's going to approximate the correct value now in some statistical sense, given that we have random points. Effectively, what I'm doing here is I'm approximating the integral with a rectangle of height equal to the average value of my function at the points, at the random points I sampled, and a width equal to the domain of integration. Okay? And importantly here, unlike with quadrature, the number of samples I have to use doesn't have to be known in advance. In quadrature, I need to know in advance I'm going to have to use 100 or 1,000 or 10,000 samples and select my intervals accordingly. Here, whenever I want, if I decide that I want to have another interval, I just sample another extra point and I keep going. So I have a progressive estimator of my integral, which is already an advantage I have over quadrature techniques. Now, compared to the quadrature, Monte Carlo allows us to overcome both of the two main critical issues that quadrature has. In particular, we no longer have a curse of dimensionality problem because the rate of convergence, the rate at which we are approximating or getting closer and closer to the correct solution, in Monte Carlo is independent of dimension. Okay, so I can increase my integral from 1 to 2 to 3 to n dimensions, and I will still converge as a function of the number of samples I draw at the constant rate. And also, I no longer have aliasing problems, because no matter how spiky, no matter how discontinuous my function is, I still have some non-zero probability of sampling the function at the point of discontinuity or at the point of the spike. Okay? So no case of dimensionality, no longer aliasing issues. So a lot of the issues we had with quadrature have gone away. Now, I mentioned earlier, and I've been saying, approximate the correct solution and get a correct estimate. What exactly do we mean with correct? This estimator I have is a random variable, because the points where I do the evaluations itself is random. So to think about correctness, I think I need to think about the properties of a random variable. In particular, I can consider the expected value, the average value I expect my estimator to have. And then if that expected value matches the integral I'm trying to compute, then I can say my estimator is unbiased. I can also consider a weaker notion of correctness by checking for consistency of my estimator, meaning that as I draw larger and larger set of numbers, do I end up with the correct solution? And ideally, my estimator should have both of these properties. The unbiased property is nice because it's one that applies even if I just consider just one sample. And conversely, I can have an estimator that is biased, meaning that even if it's consistent, even if it converges to something, it will not really give me the correct value. It's very easy to check that the Monte Carlo estimator we just discussed a few slides ago is unbiased, and it's also consistent as a follow-up of the unbiased case. So if I take my definition and I place it inside an expectation operation, I can move expectation inside because expectation is linear, and then I can plug in the definition of the expectation, move this probability P I have outside because it's constant, it's going to cancel out omega, and it's going to give me the correct value. So Monte Carlo estimators are unbiased, meaning that they give us a notion of correctness, as we'd expect of a numerical estimator. Okay? Now, of course, all of this is nice in theory. In practice, to get Monte Carlo estimators to work, I need to be concerned with other issues. For example, we are working with floating point numbers, so I still need to make sure that all operations I'm doing are numerically robust. I don't have any big numerical issues. Also, parallel implementations. Again, the Monte Carlo evaluation is embarrassingly parallelizable in the sense that it's very easy to just draw multiple samples across multiple threads and then average the results. But I still need to be careful about evaluating the function itself within each one of the threads of my GPU or of a multi-threaded processor. And lastly, the rate of convergence I mentioned earlier is an asymptotic rate that holds for any Monte Carlo estimator, but in practice, the constants that show up in this rate of convergence can be important, and in order to be able to get a reasonable convergence performance, typically I will not be able to rely on just uniform sampling of points. I will need to come up with better sampling procedures that important sample the integral. And I think Rohan and also a few of our invited speakers, Bailey and a few of our invited speakers are going to talk about important sampling later. All right, so now let's see how we use all of that, Monte Carlo integration, specifically for the Laplace PDE. And that's going to get us to the walk on spheres algorithm, a very simple algorithm for solving this specific Laplace PDE. All right. As I mentioned earlier, we have this fixed recipe for how we come up with Monte Carlo estimators for our problems. We're going to set up the PDE problem we need to solve, and not just the PDE, actually the boundary value problem we need to solve. We're going to convert it into an integral, the mean value integral in this case, and finally we're going to run Monte Carlo with a few tweaks that are going to be important to arrive at the walk on spheres estimator. The PDE we're concerned with is the Laplace PDE with Dirichlet boundary conditions, which is a function we can use to interpolate a set of conditions for a set of values from the boundary to the interior of domain. We use we set the Laplacian to 0 to enforce a sense of smoothness in this interpolation, and of course we use the Dirichlet boundary conditions to make sure that our solution is an interpol, and it actually matches the target values at the boundary. Now, the Laplacian, we are going to be working on Euclidean spaces, so it's just the sum of the second-order derivatives. We can also express it using differential operators as the divergence of the gradient of the solution. But more intuitively, we can think of the Laplacian as a quantity that tells us how different the solution is from its average value on a sphere around the point where I'm evaluating the solution. Okay? So a large Laplacian means that I have very large differences. A small Laplacian means that this difference is very small. So then what does that mean about solutions to the Laplace PD, where I force my Laplacian to be 0, for solutions that are harmonic functions, as we call them? It says that the value at the center of any sphere is actually going to be exactly equal to the average value of the solution on the sphere. And in fact, this holds not just for small spheres around the point where I'm evaluating, it holds for any sphere I can draw around the point where I'm considering the solution, so long as that sphere is contained within the domain where I'm solving my PDE. Okay? This is the mean value property of harmonic functions, and conveniently, it gives me an integral representation I can use for my PDE, for solving my PDE using Monte Carlo. So I take this mean value property, and I can now apply on it Monte Carlo estimation, as we saw earlier. How do I do that? I'm going to approximate the integral with a discrete summation over here, where the points yi will be sampled uniformly on a sphere I select around the point where I'm looking to evaluate the solution. I can use any sphere I want that is contained within the domain omega where I'm looking to solve this PDE, but it's going to be convenient to actually use the largest of those spheres, because as we'll see in a few minutes, it's going to make my algorithm converge faster. Okay? So pick the largest sphere around the point x, randomly sample on that, uniformly points on that sphere, and evaluate the solution there. Now, importantly, we don't actually know the solution on any of these spherical points we sample. So in order to be able to compute the solution at the original point x, I'm going to have to apply this estimator recursively. I'm going to go, and for every of the points I sample, repeat the same procedure, and again, express the solution as a sum of other points around spheres that are sampled around those points. But now I run into a problem. As I try to do this recursion, I quickly end up with an explosion, a combinatorial explosion in the number of evaluations and points I need to store in my memory. And really, the cause of this explosion is the fact that I have to do this branching along n samples at every step of my recursion. In fact, if I just use 3 samples, a very small number of samples in my estimator, after 16 of those steps, I already end up having to use 43 million estimators. So really, this will not work if I apply naive Monte Carlo. So what I can do to deal with this is I'm just going to set n to 1. I'm just going to use a single sample Monte Carlo algorithm, which is going to give me the walk-on spheres estimator. Take every point, around that point, draw a sphere, draw the maximal sphere I can contain within my domain, sample a point on that, and then apply recursion. And as I recurse, I end up with a random walk that jumps from one point to a point on the sphere around it, hence the name walk-on spheres. Now, I also need some way to terminate this recursion, and the way we're going to do that is use something called the epsilon cell approximation. That basically says that if my random walk reaches a point that's sufficiently close to the boundary, closer than some threshold epsilon that I get to select, I'm going to approximate the solution there as being equal to the Dirichlet value that I get from my boundary conditions. Okay, and remember, this is going to be very important when we check whether this estimator actually works. So that's it. It's a very simple procedure. Keenan will do a tutorial later for how to efficiently estimate this, but it's going to give me a solution like that as I draw more and more samples, converges to the correct solution I expect for this PDE problem. And if, again, you're coming here with a background in rendering, or if you've taken any intro to graphics class, this algorithm may remind you of the ray tracing procedure we use in rendering to simulate light transport, where, again, we have a recursive estimation, where at every step of a recursion, we do a geometric query. In ray tracing, that's shooting a ray and intersecting the scene. And then at that estimation, we do some amount of compute to continue until we can terminate either at the light source in ray tracing or in the epsilon cell in the case of walk-on spheres. In both cases, we end up with these conceptually very similar algorithms exactly because we use this recursive Monte Carlo procedure to estimate the integrals. Now, does this work? Does this actually give us the correct answer? We already saw earlier some points about whether Monte Carlo estimators are correct in some sense, right? We saw unbiasedness properties, but those were about algorithms that are not recursive. Here we have this extra recursion step that should make us worried. Whenever we have this recursion, does it terminate? And when it terminates, does it actually converge to the correct solution? So here, since we're approximating this integral, essentially what we are asking is, if I go and apply recursion on this integral, will the integral after an infinite number of recursions exist? And to get some intuition about how to think about this problem, we can look at an analog from linear algebra. This integral is nothing else than an infinite dimensional version of a matrix vector product. So effectively what I'm asking is, if I have a vector x and I multiply it by a matrix A, and then I raise this matrix to the kth power because I'm doing multiple multiplications, does that limit of A to k going to infinity exist? For that, I'll need to be able to have a matrix A that doesn't make the vector larger at each step, by which I mean it doesn't make the norm of the vector greater after every multiplication. If it keeps making it larger, then eventually the whole thing will explode as k goes to infinity. And we can make the similar, we can write down similar notions for the case of the integrals, replacing norms of vectors and norms of matrices with norms of functions, in this case the solution function, and operator norms for the integral operator we're applying. All right? Now here is the problem. This mean value integral actually does not converge on its own, because its operator norm is not smaller than 1, it's 1. And we need it to be smaller than 1, so we shrink. So if we're just applying Monte Carlo integration, single sample Monte Carlo integration, to this mean value integral, we would actually end up with an estimator that doesn't converge. And we can see that because if we just do that, we never terminate. We have no way to figure out when to terminate. But what saves us from this problem is this approximation I mentioned earlier, the epsilon cell approximation, that says that if I get close enough to the boundary within the epsilon cell, I'm going to stop recursing and I'm going to approximate the solution using the boundary condition. I can think of this in the context of the integral representation over here by just splitting my integral into two parts. One for the part of the sphere that's outside the epsilon cell where I use recursion, and another for the part of the scene that's inside the epsilon cell where I replace recursion with the boundary condition. And now, as soon as I do that, I end up with a recursive operator, an integral operator that now has a norm that's smaller than 1 and therefore converges. If you're working in rendering, we have similar theoretical arguments there from G. Marvo's work back in the 90s about why ray tracing converges. Essentially, so long as we have a tiny bit of absorption at any one of our ray tracing iterations, then we will end up with a convergent ray tracer. If we have all of our scene made up of mirrors or BRTFs that are perfectly reflective, then we don't get convergence because we have the same problem over here of an operator not being equal to 1. It's exactly the same story here, that thanks to this epsilon cell acting like an absorber, essentially allowing us to converge. Okay? Now, we need this epsilon cell to be able to converge. We need it to be able to terminate our estimator. It's an approximation. It's not really something that's there in the PDE solution. So the question is, how important is it? Well, in practice, we can find empirically that playing around with this epsilon value doesn't introduce very strong bias in our solution, and also doesn't have a very big impact in terms of the number of walks we need to reach until we arrive at the boundary. In fact, we saw here this on one toy example, but people have been able to come up with formal arguments to actually show that. So Binder and Braverman have proven that given any kind of geometry that's at least smooth or maybe convex, we'll be able to converge to the boundary within a number of steps that scales logarithmically as with the inverse value of epsilon. And this becomes very important when we start considering applying our algorithm to geometries to domains that have very fine detail, very fine geometric detail. If I was trying to approximate the solution to the PDE using tetrahedral matching or any kind of discrete algorithm like what Keenan mentioned earlier, using quadrature effectively, for these kinds of geometries, I would end up with a complexity that scales very badly with epsilon. If I change my epsilon by an order of magnitude, I will end up in 3D increasing the number of compute and memory I need to use by 3 orders of magnitude. Whereas here, thanks to this logarithmic complexity, I can make my epsilon very small as the geometry, and still get a very small impact in terms of the compute and memory I have to use to solve my simulation. Okay? So with anything other, with quadrature, I end up with epsilon very quickly exploding in terms of memory and compute, whereas here I end up with much better convergence. Now, that doesn't tell us the whole story. This just tells us how many steps I'm going to need to be able to approximate the solution, but also need to be worried about how expensive each one of these steps are. And the main cost for each of the steps is performing this closest point query to find what the largest sphere I can draw is. Now, these closest point queries are very similar, in a sense, to the ray tracing queries we do in rendering, in that we can approximate them, we can accelerate them, using very similar techniques like what we do in ray tracing. And to give you some idea about how that works, let's take a look at a very simple closest point query we can do for a linear segment. In this case, the answer is just the orthogonal projection of a point, of the query point to the segment, plus some additional logic for cases where the closest point is at the edges of the boundary segment. If I have two of these segments, then the answer will be the minimum of the distance between the two segments, between the point and the two segments. And if I have a whole bunch of those, instead of just considering a for loop that goes over each of the segments and computes the minimum, I can now start bundling them together in some bounding volume hierarchy that will allow me to very quickly throw away a lot of those points, groups of those points, without having to evaluate all of their members one by one. So by using bounding volume hierarchies, I can perform these closest point queries on geometry such as meshes at a logarithmic complexity with the number of primitives I have in my geometry. Okay? These bounding volume hierarchies are exactly the same hierarchies we use to accelerate ray tracing queries, and therefore we can already leverage the very extensive research that's been done in rendering, accelerating, building these processes, and amortize a BVH or any other kind of spatial hierarchy to make our nearest point queries very fast. Now, the fact that our algorithm interacts with the scene only through these closest point queries without requiring any other kind of interaction with the geometry gives us a few other advantages. For example, instead of just working with meshes, like this mesh that Keenan showed earlier, we can work with any kind of geometry representation that supports closest point and empty sphere queries. For example, we can use it for sign distance, neural, or harmonic implicit functions. The last two are functions that very recently in computer graphics, we have found out algorithms that allow us to do different types of geometric queries for them, including closest point and empty sphere queries very efficiently. So overall, by using Monte Carlo, we end up with a PDE solver, in this case for this very specific problem, the Laplace PDE with Dirichlet boundary conditions, that has all of the same properties that we have come to be using and taking advantage of in the context of Monte Carlo rendering, geometric flexibility. And I'll go through each one of these properties. We have correctness in the sense that as long as our equation is well posed, we're going to end up with a numerical solution that approximates the correct value. We have scalability, will be very easy thanks to the fact that we're using these spatial hierarchies and thanks to the logarithmic scaling of both the epsilon cell approximation and our queries to scale to very, very, very large geometry with a lot of detail and huge scale. Have great parallelism in the very same way we can parallelize ray tracing, we can parallelize PD simply by running multiple instances of the walk-on-spheres algorithm on the GPU and averaging the results. We have progressive evaluation. This is a great feature. I can very quickly get a noisy but still useful estimate of my solution so that I can iterate. Maybe I want to change my viewpoint. I want to change my shape. I don't need to wait for a measure and then a full solver to give me the solution. I'll just get a noisy preview and then move on. I can deal with geometry that is very general. It's very easy to mix and match different geometric representations, all of which support closest point queries without having to convert one to the other. And of course, I have robustness, a point that, again, we've made a few times so far in this course. If my mesh has self-intersections, holes, and so on, I will still get a pretty reasonable estimate of my solution. All right? So to finish my part, I'm going to highlight that with the walk-on-spheres algorithm, these grid-free methods, even though in computer graphics they have only attracted a lot of attention in the past 5 years, they actually have a pretty long history. So even from the early 20th century, Einstein has been looking at how to simulate Brownian motion for the heat and Laplace equations. The walk-on-spheres algorithm actually was introduced in 1956, 60 years ago by Mervyn Muller. And since then, it's been reinvented, who highlighted that it's a great algorithm because it allows us to solve problems, regardless of how complex the geometry is. Since then, it's been reinvented a few times, for example, called the floating random walk. And then there have been quite a few other papers that deal with complexity analysis, extensions, and applications to circuit design, porous media, and so on. But their use still has been quite limited, exactly because of the fact that they are very, very limited the types of PDEs they can solve. just the Laplace PD with Dirichlet boundary conditions. So in the rest of this course, we're going to be seeing ways to generalize these methods to other more general PDs, more general more general types of boundary conditions, as well as new applications enabled by all of that. So I'm going to stop here. I'm going to hand it over to Keenan, who's going to do a tutorial on the walk on spheres method.
All right, so because I know it can be hard to sit through a long lecture, and because this is supposed to be, a course, not just a bunch of SIGGRAPH talks, we are going to do something interactive. How do I do this? Or we're just going to look at this slide for a long time.
There we go.
All right. Let's see if we can get this going here. Okay, and I'm going to go through this pretty quickly, but this is going to be some interactive coding where we're going to see that you can actually build up one of the solvers Ioannis was just talking about from scratch in your browser in a few minutes. If you've ever dealt with like finite element methods, this sounds crazy. A guy's going to get up on stage and code a finite element solver, right? But we really are. We're going to build hopefully we get to it, a Laplace solver right before your eyes using nothing more than the features available in the browser. Yeah, if you want to try this out, if you want to read this at a more leisurely pace, URL is up there. There's a QR code. I'll leave this for just a few more seconds for people. I see people still have their phones up. All right. And OK. So as I said, there's a lot here, and you can spend a long time going through it if you like. But our basic setup, just to give some physical motivation, I don't know how much you all know about cars, but inside your engine, between your engine block where you're actually combusting fuel and a cylinder head where you have the spark plugs, you have this thing called the head gasket. And you can read about what this is for. But basically, it can get really, really hot, and you might want to do an analysis of, well, just how hot is it getting and where, because I want to avoid failure. I want to know where are the points in this domain where things are going to go bad, and then maybe I want to adjust the design of that domain to improve the thermal characteristics, right? I want it to hold up a little bit better. Okay, and so we're going to solve a Laplace equation on this domain, again, using our simple implementation here. One thing I would point out about this is, well, first of all, we're not going to build a mesh like this, right? I'm not hiding a triangle mesh anywhere in this example. The domain is really made up just by its boundary curves, and something that's interesting is a lot of common 2D CAD formats can make some pretty complicated geometry using, actually this picture is nothing more than circles, straight lines, and circular arcs. So it looks quite complicated, but it's actually a very, very small number of geometric primitives. And the nice thing, as Ioannis just mentioned about these walk-on-sphere solver, is I can solve directly on this concise boundary representation without converting it to a polyline, without triangulating it, without doing all the usual things that we do in simulation. Okay, so we're going to see exactly how that works. So this is all going to be done in GLSL, kind of like shader toy, if you have experience with that framework. And we're going to be writing little shaders that determine what color of pixel to light up at every moment. So each of our pieces of code over here is just going to say, given a coordinate x, y in the image, what should I do to give it a color? Okay. Okay. So the basic thing we need to do, as we talked about, is how do we incorporate or how do we describe our domain geometry? Again, I'm not going to take the finite element route of giving a triangle mesh. I'm not going to take the finite difference route of describing it as a subset of voxels on a grid. I'm going to really just have some really basic data structures, circle, segment, arc, that give the basic geometric information. A circle is a center and a radius. A segment is a start and an end point. An arc is maybe a start radius and start and end angle, and so on. You can let your imagination go wild. We don't have to just use these shapes. Okay, and so given this setup, we just have our domain is described as a few arrays storing some circles, some segments, and some arcs. This is obviously more simple than our cylinder head gasket up there, but some kind of geometry. Okay, to make use of this, we actually have to be able to query the domain geometry. And as we've emphasized a few times, really the only thing we need to know is for any point in space, what is the closest point? I've got a picture of it up here, right? So for any given query point x, what is the closest point on the domain boundary? Okay? So for instance, in this case, the closest point happened to be a circle, but it could have been a segment or an arc or something else. All right. So let's get going. I told you we're going to do this from scratch. I'm really gonna code this up. So I'm going to tell you, okay, how do I compute the distance to a circle? Hopefully that's within your mathematical, capability. I give you a point, let's say P or X. I know the center of the circle. I know the radius of the circle. How far is P from the circle itself, the red curve. Okay, that's going to be something like, well, the distance from P to the center minus the radius. And then I take the absolute value of that, right? So we can code this up in our little framework here, right? So to do compute and return the actual distance to the circle, let's do it. Okay. So I might say, first I'll just compute the distance to the center. So let's see, length of x minus c dot center. Okay. Oh, yeah. Okay, so then I can say maybe return d. And that's not the right formula, but let's just hit compile and see what we get. Okay, there we go. So we have, plotting the distance, we actually get the distance to just the center and not to the circle. So what should we do? Well, maybe we should, as I said we would, oops, not do that. Excuse me for a second, I should have done this ahead of time. Okay, forget it. I'm just gonna live with it. Okay, so we've got the distance to the center, and if I subtract the radius, so circle dot r, then I get a syntax error on line 10. Oh, thank you. It's like extreme coding. Okay. Oh, and it's not called .r, it's called radius. All right, there we go. So do we have this distance to the circle here? Not quite. We have the signed distance to the circle. Okay, it's negative inside and positive outside right now. Now, I know a lot of people like to compute signed distance, but for walk-on spheres, we don't need that. We actually need the unsigned distance. We need to know what is the largest empty sphere we can use that stays within our domain. So I'm just going to return the absolute value of the signed distance in this case, and I get the unsigned distance. There we go. We could walk through this, for different types of primitives, right? Distance to line segments, again, has some simple formula that Ioannis mentioned. One thing I'll say about this code tutorial, if you ever get stuck, you can cheat. You can just hit, here's the reference solution, okay? And it'll show you the reference solution, and we can check, yep, we got the right distance to a segment, and we can check that out for a bunch of different endpoints to see we got the right distance formula, okay? Likewise, distance to circular arcs, we have to do a little bit more trigonometry, but in the end, we get a nice formula for the distance to a circular arc, and it works quite well, for any arc, right? And again, I'll emphasize, if you were trying to do a circular arc, even a single circular arc with a finite element solver or finite difference solver, what do you have to do? You have to, break this arc up into lots of little pieces and decide, well, how much, accuracy do I need in my solver, and therefore, how many pieces do I need to chop it up into? And, there's all these parameters that you simply don't have to deal with here. Okay? Okay, so the more important thing is how do we put this together to get the distance to the whole boundary? Okay, well, the beautiful thing is that this is very compositional. If I already have methods that give me the distance to individual objects, distance to a circle, distance to a segment, distance to an arc, what do I need to do to get the distance to the whole boundary? I just take the minimum over all those primitives. Okay, so I might say something like, I start with the maximum possible distance. Okay, and then I'm going to loop, let's say, over my circles. So for I equals 0, I is less than n circles, I plus plus, d equals min of d, and I'm going to get a few errors here probably, but let's see, distance circle between x and circle I. And there we go. Let's try compiling that. And nothing happens. Okay. I didn't return, okay, yeah. It's not complaining because it's doing something but not the right thing. Return D, thank you. Can you all come with me while I code in the future? It'd be great to have you around. Okay, there you go. So now I took the minimum to the distance of all those circles, and you can see already, we have a more interesting domain boundary, just the circles. Okay, so let's do the same thing for the segments as well. This time I'll get it right. Okay. Hit compile. All right, so I get the distance to the circles and the segments, and finally let's add the arcs. All right, there we go. Okay, so quite easy to get that distance query. That's the fundamental thing we need for our walk-on sphere solver. In fact, it's the end of our geometry story. We're not going to do any meshing. We don't need to implement any other queries. We can now handle all sorts of CAD, 2D CAD files. In fact, we have a little conversion tool that'll convert a DXF file into a list of these segments, circles, and arcs. Okay, so now let's go on and actually estimate the solution to the Laplace equation. So remember, we want to solve Laplace u equals 0 on the domain, subject to u equals g on the boundary. And this is kind of the perspective of finite elements, as people say, oh, I take this PDE and I just run with it. The walk-on spheres perspective says, hey, there's a different equivalent way I can write the solution in terms of an integral. Or if I really want to put it concisely, I just say the value of u at any point x is the mean value of that same function u over a sphere or circle around the point x. Okay? So my basic task, as Ioannis mentioned, is I want to evaluate the integral over that circle divided by just the size of the circle, the perimeter. How do I estimate an integral? Well, I could just take a bunch of points uniformly, sample them. I could space out evenly points on the circle and sample those, but that would be a lot of work. So what I'm going to do instead is do this recursive estimation that Ioannis mentioned and just draw a single random sample from the whole circle. Okay, use that as my estimate of the average. And then because I don't know the value at that single sample, I have to invoke my recursive estimator again. You see? So as I take each one of these averages, I need to know a new point to compute a new average, and so I get a sequence of points in my domain, which I can think of as sort of a random walk in the domain. Okay? Something like this. And so I start at x0, I sample one random point to get an average over this first circle, I get x1. I take one random sample to compute an average over the second circle, I get x2, and so on. So let's write some code to do that. And actually, just because it'll help with debugging, we're going to visualize the path that we take. And we're going to kind of do a cute thing here. We're going to use the distance functions themselves to visualize the walk. Okay? So we'll see how that works in a second. But let's start out by just implementing this walk. All right? So we're going to start out and say, okay, where am I? My point my point that I start out is just x naught. Okay? I loop over the maximum number of steps I want to take for step equals 0, step is less than n steps, step plus plus. Okay, I need to do something. Well, the first thing I need to do is compute the distance to the boundary. Hey, we just implemented that method. Okay, so I can say float d equals distance boundary x. Okay, and then actually I'm going to check, am I already done? Am I close enough to the boundary that I can stop and just grab the boundary value? Okay, so I'll just check if d is less than epsilon. Oh, what is epsilon? Well, let's define it. Okay, then we're close enough to the boundary and we can stop. All right. Okay, here comes the interesting part. How do we take a step? Well, we already know the distance to the boundary. We can't walk further than d, and we just want to walk in any direction. We don't care. We're going to randomly sample a direction. So I'm going to compute an angle theta, which is this 2 pi times a random number between 0 and 1, which is in this code framework called unit rand. Okay? And then I can say x, my next point, is equal to my previous point plus the radius of my empty sphere, d, times, and just cosine theta, sine theta. All right? Now if I do that, nothing's going to show up. Maybe it won't complain. Oh, it'll complain. Okay. Nothing's going to show up because I haven't changed any pixel values or anything. So let's actually draw something on the screen. Okay, let's draw the segment connecting each point and the next point. Okay, so for that I need to write a method draw segment, which I'm just going to crib from this one that's drawing our boundary geometry here. And it just says, okay, I compute the distance. Oh, maybe I call it, yeah, draw segment. And I've got two endpoints, A and B. And I compute the distance, the segment from A to B. Okay, and if the distance that I compute to that segment is less than my line width, I'm just going to color the pixel black. That's all this method does. So down here, what am I going to draw what am I going to draw a segment between? I'm going to draw it between the two consecutive points on my path. So I probably should store the previous x. Okay, and so I can do that before I take a step. I'll draw this segment. Draw a segment. X last, and update my last segment after I draw that. Let's see if that worked. Last X last, okay. Okay, anybody want to fix my bug? So what I get now is I get a sequence of points, but I don't get segments. It looks like I'm just drawing the thing from the. Ah, I see. I need to draw the segment after I update the current position, but before I overwrite the old position. Okay, there we go. Okay, so now we have a walk, right? And if I want to see which circles I'm sampling those points from on my walk, I can do something very similar. Okay, draw a circle, right, using a center and a radius. Maybe make it a little thinner just for visualization purposes. Okay, and so I can also draw the circle with center x and radius d, so the largest empty ball that I can sample from. Let's see, 115. Oh, I need to compute the distance to the circle. I'm sorry? Ah, thank you. Other way around. Great. Okay, now it seems that I've done something slightly wrong. I've put the sphere center at the wrong place. Let's try doing that. Okay, cool. So now something interesting happens, right? I can visualize my random walk. I can move the starting point around here. I'm just using the same random numbers no matter which starting point I have. And I can see really what these walks look like. And I can also, if I hit play here, I'll just use some different random numbers to take different random walks, right? And this kind of visualization can be really nice. It also kind of gives you a hint at what we're up against when we're writing these kind of solvers. Just like in global illumination, where I'm bouncing rays all around the scene and have to worry about the fact that these rays are very incoherent, in walk on spheres, I'm often taking these very incoherent walks around the scene. And so now if you want to talk about high performance Monte Carlo, you have to think about things like caching and we can hopefully leverage all the strategies people have developed in Monte Carlo rendering to do that in an intelligent way. Let's say you're doing this on a GPU or whatever. Okay? Now the good news is, actually, I'm almost done writing my solver, even though I spent a lot of time on the visualization. I'm just going to copy this code, because computing the walk, that's kind of the main thing I have to do. Okay, and we're going to go down here. We're going to go back to our original domain, the cylinder gasket, and we're actually going to solve the Laplace equation. Okay, so where is the method that we have to implement? Implement the Laplace estimator. Okay, so I'm going to paste this in. We don't need to, we're not going to visualize our walks anymore. We can get rid of all this, draw segments. We can get rid of this x last and so on. Okay, what we need to do instead, rather than drawing a walk, is we just need to know what is the value at the end of our walk. Right? The whole point of this Laplace estimator is I take a random walk until I get to the boundary, I grab the boundary value, and then I average all those boundary values over a bunch of walks. So what should we do? Well, when we break out of this loop, we need to do nothing more than return the boundary value at x. Okay, and I'm cheating here just for the sake of time. What does the boundary value function do? Very much like our drawing function, it just loops over all the primitives and says, give me the value of the closest primitive. Give me the boundary value for the closest primitive. Okay, so I lied a little bit. We didn't implement 100% of this on stage, but okay, the structure of this function is not much different from what you did to draw the boundary geometry. Let's see if this works. Hey, amazing. So what we're looking at here is our cylinder head gasket. Each component, like each circle, segment, and arc, has a boundary value, has some constant assigned to it. And at each pixel, we've taken one of those random walks that we computed before to the boundary and just grabbed the boundary value. In fact, this is the solution we get by just taking one random walk per pixel. Okay, so already you're getting a pretty good sense of where the temperature is. This is that promise of Monte Carlo that even if the solution at this moment is not very accurate, in an instant, I already know very, very well which things are hot and which things are cold, and I can iterate on my design. And if I want to improve the solution, I can hit play here, and it's just going to average more and more solutions to get a more accurate, or more and more walks to get a more accurate solution. Okay, so that's it. That's our Laplace estimator with walk-on spheres, and I'm going to turn it over now to Bailey, who's going to talk about some more interesting PDEs we can solve. Thank you. Gonna help with that.
Awesome. So yeah, so far hopefully you've been convinced that there are some interesting benefits of these Monte Carlo solvers, but perhaps you're left like a little unsatisfied with the fact that really so far we've only seen a single instance of a PDE with one type of boundary condition that we can solve. So a lot of the work of working with these solvers is they have a lot of power, but it's pushing them to new PDEs or extending them to new PDEs and boundary conditions. And so we'll see in this part how to handle the Poisson equation. And then in the next part that I'll cover, we'll talk about Neumann boundary conditions. And this will really broaden the scope of PDEs that we're able to solve with walk-on spheres or similar methods. Yeah, just like readjusting so you can see them. Okay, so most real-world systems are not entirely determined by what's happening on the boundary, but they actually have sources of heat or electrical potential inside of the domain, right? So each of you sitting in this room is actually acting as a heat source, for instance. So if you wanted to design a building or auditorium with an efficient HVAC system, you'd actually need to account for these types of sources. And similarly, these sources will show up in places like chip design, where you have lots of wires or components on a circuit board that are going to have a very significant impact on the temperature of the circuit board. So we're going to follow a roadmap that is very similar to the section that Ioannis covered on the Laplace PDE, where effectively we start by writing down the equation or the PDE that we want to solve, and then we try to figure out how we can express this differential equation as an integral. And once we arrive at an integral, like the Green's integral here, then really the last thing we have to do is develop an estimator for that integral. And we'll follow this recipe both in this section and the next one. So in the last section, we saw a Laplace PD that looked something like this. In the thermal setting, you can think of this Dirichlet boundary as prescribing some sort of a temperature on the boundary. And the Laplacian, again, is just interpolating this temperature smoothly to the interior. Now, though, we want to consider the addition of a source term, f, which is going to be referred to as the Poisson equation. Now, you can think of this term as a heat source in the domain, such as a body giving off heat or a hot component on a circuit board. And because of the source term, the solution U is no longer harmonic, so we're not going to be able to directly apply the mean value integral like we did before. We're going to have to do something else here. Just to build on the intuition, though, for how these equations can be generalized into a more general mean value integral, let's step through step by step like what happens as we make the source term more complex. So if we just start with the Dirac delta source term in free space, we can write down a closed form solution to this PD actually, and this PD is, or this solution is referred to as a Green's function or a fundamental solution. And you can think of this solution as just specifying how much heat will be transferred from a point Z to every other point in the domain. So if I touch a needle to Z, how much, or what's the temperature everywhere else in the domain? And we have a closed form solution for this. And we can go and make this solution a little bit more general by considering the Green's function or the solution to this PD on a ball. And so in this case, the only difference is that we restrict the boundary of the ball to have a constant 0 temperature, where you can essentially think of that constant 0 temperature as an idealized absorber of heat. Now, since source terms are additive, we can actually model two heat sources in the domain just as a sum over these Green's functions for the ball. So now we have this function W that will represent the total heat at a point X as a result of touching a needle at point Z1 and Z2. And now the final step that we're going to take here to generalize to a continuous source function and not just these delta functions is to just integrate over these Green's functions. And so here we now have a way to describe the influence of a kind of continuous source term, the influence of that continuous source term at every other point in the spherical domain. And we'll refer to this as the Green's integral. Now, the Green's integral over a ball will act as a correction term for the mean value integral. And this will enable us to have a generalized mean value integral for Poisson equations. So we have the same mean value integral as before, which incorporates the boundary data. But now we also have this Green's integral term. And this is going to incorporate all of the effects of the source terms that fall within the ball. So from the former section, we essentially know how to estimate this first integral by taking a recursive random walk. And the second integral is actually a lot simpler to evaluate. We just have to generate a single sample inside of the sphere, and we can use that single sample to form a single sample Monte Carlo estimator of the Green's integral. And so what happens to our walk on spheres method? Well, it's identical to before, except for the fact that we have one additional sample that we take inside of the ball at each step of the walk. And we'll sum up the contributions from these samples as our walk progresses. And that's all we need in order to extend to this much broader class of Poisson equations. So overall, the changes you need in code are actually even simpler. It's just 2 lines of code, right? At every single step, we'll generate a random sample, and then we'll add a contribution to our current estimate. But we're not quite done here. So far, we've kind of been using uniform sampling of the domain, at least implicitly, which is going to yield a set of sample points that look something like this. And while this is going to give us an unbiased and correct estimator in some sense, it's perhaps not incredibly efficient, right? We're going to have a lot of samples which fall in places where the Green's function is going to be very small, so those samples won't contribute much. Or they may fall in places where the source term is 0. So if we just use uniform sampling, we're going to waste a lot of samples on regions that don't actually contribute much to the solution. So how can we work around this? Well, instead, we want to avoid sampling points in regions which don't contribute much to the integral. So we're going to sample from a distribution which approximates the integrand. Now, if we sample from this distribution, we also have to slightly modify our estimator to account for the fact that we're undersampling in certain regions in the domain. Now, in our Green's integral case, if we start to sample proportional to the Green's function, we're going to end up with a sampling distribution that looks something like this on the bottom row, where you can see that we end up with a lot more samples concentrated in regions where the Green's function is larger. And so this is going to improve our sampling efficiency. Now, when I talk about improving our sampling efficiency, what I really mean is we're reducing the variance of our estimator. And the variance of our estimator is just a measure, essentially, of, on average, how far the estimator is from the actual ground truth estimator value. Now, to actually go and analyze this variance and see what we can do to influence it, we can just go and write down the expression for, or take the variance of our estimator, our important sampled estimator, and we can perform a few algebraic steps to basically arrive at this expression in the bottom row, where you can see that there are only two quantities that actually impact the variance. The first is going to be the number of samples we take, n. So we can reduce variance by taking more samples or by taking samples or evaluating samples more quickly. But aside from just throwing more samples at this problem, really the only other lever that we have here is to take more intelligent samples. So we want to sample from a distribution P which approximates the integrand. And if we do so, we'll achieve a sort of optimal estimator in some sense. Now, if we go and use the importance sampling for the Green's function, which we discussed earlier, you can see that we'll converge to a much cleaner solution. There's a lot less of this typical Monte Carlo noise. And if I actually go and freeze this at 128 samples and zoom in, you can perhaps see this difference is a little bit more stark. And if we bump up the number of samples, you'll see that the uniform sampling approach actually really struggles to converge to the correct solution, whereas if we just importance sample from the Green's function, we're going to get much nicer results. And this sampling from the Green's function doesn't necessarily cost more compute-wise. It's a very small price we pay to get a significant reduction in variance. Now, you can play similar tricks by trying to importance sample from the source term rather than the Green's function. So for instance, if we have this S-shaped source term, I can try to concentrate all of my samples inside of that region. And across all these cases, you may be wondering, how do I actually generate those samples? And we won't go into a lot of those details in this course, but just to give you a really high level, there more or less are two ways that we generate samples when we're working with these methods. Either we use rejection sampling, so we generate a bunch of samples from a known distribution, and then we'll throw out samples inversely proportional to the target function. And the other approach we have is we can warp samples. So we sample from a known distribution, and then we essentially try to transport those samples to something that resembles our target distribution. Now, finally, we often don't have just a single sampling strategy that we want to use. Even in this simple example of the Green's integral, we have the Green's kernel and the source integral, which we want to evaluate. So in practice, how do we incorporate many different sampling strategies? And you can think of this as through the metaphor of a goalie, right? So a goalie has to block the ball coming into the goal, and he has kind of two strategies. He can jump to the left or he can jump to the right. So if you go to the left, you can think of this as one strategy. The ball may be there some of the time. Maybe other times the ball will go off to the right. So rather than just pick one strategy, perhaps the right strategy is to just, on average, kind of jump to the left or jump to the right, like flip a coin and decide which way to go. And if you use this mixture strategy, which goes by the name multiple importance sampling, you can start to combine many different sampling strategies and construct kind of an aggregate, robust sampling method. So I think, are we going to skip past the, OK. So Keenan has, similar to the section on the Laplace PD, a whole section in the walk-on spheres in one weekend for the Poisson equation. So you can go step through that tutorial and essentially see how to go implement this extension yourself. Now, though, we're going to discuss another pretty interesting and rich class of PDs, or rather boundary conditions we can extend to by discussing Neumann boundary conditions. So recall that walk-on spheres is just using the largest empty ball that's tangent to the boundary to solve the Laplace and the Poisson equations. However, a really big limitation of this algorithm is that it only handles Dirichlet conditions, which prescribe fixed values on the boundary, as you can see through this kind of simple example here. But what if we also want to handle Neumann conditions, where rather than interpolating these fixed boundary values, we want to interpolate between prescribed derivatives? Now, Neumann boundary conditions are actually fundamental for a huge number of applications. So in fluid mechanics, they're going to describe the velocity or pressure gradient at an interface. In structural analysis, they can prescribe surface traction or stress. And in thermodynamics, they correspond to heat flux across the boundary. And so physically, this means that if the normal derivative is 0 on the Neumann boundary, then the boundary is insulated and heat can't pass through the boundary interface. It's contained entirely in the domain. So really, we have this rich class of different phenomena that we can simulate with Neumann conditions. And so we want to see how we can modify walk-on spheres to incorporate these conditions. So because Neumann conditions prescribe derivatives, that means that if we use the slope h to extend the function slightly beyond the boundary, then the extended function will essentially have mirrored values on either side of the Neumann boundary. And intuitively, this suggests that maybe our random walk should be mirrored or reflected across the Neumann boundary as well. Now, a naive strategy then is to randomly sample the biggest sphere that crosses a single edge on the boundary and essentially perform this reflection across that edge. So we reflect a point back into the domain across this edge. But this approach quickly becomes really inefficient as the resolution of the boundary increases. Now, we could try to use a bigger ball, but if we do this without accounting for the curvature at all of these vertices, then we'll necessarily have bias in our solution estimate. And this is going to negate a key strength of walk-on spheres, which is that it can simulate random walks in a mostly unbiased way. So far, the only bias that we've actually seen is, or the only place bias is introduced, is through the epsilon shell. Another option that you might consider is to just push the random walks back into the domain a little bit by a small fixed distance every time they enter the epsilon shell around the Neumann boundary. So this kind of captures the behavior of a reflecting boundary, but it has two problems. So first, the walk lengths are going to become extremely long because the boundary will serve as an attractor for walk-on spheres, and we'll just keep reflecting off of it. And each of these reflections is going to accumulate a little bit of bias, because in order to perform this reflection, we're essentially approximating the normal derivative at the boundary with finite differences. So we want to bypass these issues, and so we're going to have to look for another method that kind of goes beyond just thinking about this problem in terms of walk-on spheres and the standard mean value integral relation. And so in particular, we're going to consider a different integral formulation for harmonic functions, which is called the boundary integral equation. So much like the mean value property, we have the value u, which is the unknown solution, whose value is only known on the Dirichlet boundary. Now, this BIE also will give us a natural way to incorporate non-zero Neumann conditions, because as you can see, it includes the normal derivative of the solution. And we'll know this value on the Neumann boundary. And here we additionally have, beyond just our boundary values, we have a Green's function g, which is the fundamental solution for our PDE. And we separately have the kernel p, which is just the normal derivative of g, which you may have also heard referred to as the Poisson kernel. So now we kind of are back into this same recipe or strategy from before. We started from a differential expression, and we have an integral equation. Does that mean that we just have a Monte Carlo approach to Neumann problems, right? In the last section we saw, we could more or less just write down the integral, and the estimator became very clear. It was immediately obvious what we should do there. But here, it's not quite that direct for a couple of reasons. So first, the solution u isn't known anywhere on the Neumann boundary. So we have to figure out how to resolve that. And in a similar manner, the Neumann data isn't known on the Dirichlet boundary. And then finally, or I guess finally, we have to actually sample this integral. And we don't necessarily have a sampling strategy that will work for both of these kernels yet. And in general, I told you we have the Green's function and the Poisson kernel and their fundamental solutions to the PDE. But for arbitrary domains, we don't actually know what these functions are. Solving for them is as hard as solving for the initial PDE. So we're going to address these issues one by one, and we'll see how we can take this integral expression and turn it into a random walk method. So the place where we start for this is by looking at the Poisson kernel and the Green's function. So while we don't know these for arbitrary domains, they are analytically defined for simple domains, such as a ball or a free space. So we can start by considering using kernels for the Green's function or the Poisson kernel for these simple domains. So suppose that we took the domain omega, and we assumed it was an empty ball. then inside of this boundary integral equation, the Poisson kernel is going to be uniform. And the Green's function will happen to be 0 over the boundary of the ball. And this means you actually arrive back at the mean value integral, which we use for walk-on spheres. And what this really is implying here, and what you should take note to, is that we don't actually have to solve this boundary integral over the entire domain. We can instead think of solving it over subdomains. And we can specialize it not just to spheres, but any subdomain A that contains a point x. So for a Laplace equation with 0 Neumann boundary conditions, the solution ends up equaling the integral of a Poisson kernel of this subdomain A times all of the unknown solution values on the boundary of A. And we can think of this equation as a generalized mean value property over subdomains rather than spheres. Now, the next idea then is to take a walk on these subdomains. And these subdomains can contain parts of the Neumann boundary, and we can essentially just repeatedly sample the Poisson kernel and keep evaluating the solution value using the subdomain integral. Notice that we now take large steps away from the boundary, so this fixes some of those problems we noted before with reflections. But how do we actually pick the next random walk location? So recall that the Poisson kernel isn't going to be uniform over the boundary for an arbitrary region. Fortunately, there's an even more general version of the boundary integral equation where we can take any two sets, A and C, where we integrate the Poisson kernel of C over the boundary of A. And this gives us a lot more options to design our algorithm. So in particular, we can first choose C to be a ball, which is essentially a Poisson kernel that we'll know. And if we're standing at the center of that ball at a point x, then the Poisson kernel evaluated at a point y is the familiar sine solid angle. And so here we have n as the normal to the boundary at y, dotted with the direction towards y, times 1 over the squared distance from x to y. And intuitively, this sine solid angle is just the size of the shadow cast by the boundary on a unit sphere around the point x, which takes into account the relative orientation of the boundary and the sphere. And you may recognize this sine solid angle as the kernel of the winding number integral, which will measure the extent to which we're inside or outside of the domain. For any watertight domain, we can also just compute this integral by shooting a ray in a random direction and returning the number of hits in that direction. So if you're inside, the number of hits will be odd, whereas if you are outside, the number of hits will be even. This same solid angle actually shows up again in the integrand of the rendering equation as the geometry term, where it multiplies the BRDF, the incoming radiance, and the visibility between any 2 points x and y. So in Monte Carlo rendering, we generate samples y on the scene just by tracing rays and returning the first hit. This will sample, actually, the geometry term and the visibility term. But note that in the boundary integral equation, we don't have a visibility term, but this isn't necessarily a problem. We can still import and sample the solid angle just by shooting a ray in a random direction to get the next walk location. So now we have a way to sample the Poisson kernel. We're just going to shoot rays like we would in rendering and take all of the hits that we get along the ray. But we actually need to choose the subdomain A for our boundary integral equation. Now, if we just choose A to be the entire domain, which seems kind of appealing to do at first because we immediately will have steps to get to the boundary, we run into the problem that we'll have to recursively evaluate the solution at every intersection along a ray. Remember, we don't have a visibility function here. And this isn't something that we want to have to do because we're going to end up with exponential growth in the number of points that we need to track with each level of recursion. So instead, we're going to let A be a star-shaped region, meaning that every point on the boundary can be seen by an arbitrary point at x. If we then sample according to solid angle, we're only ever going to have a single intersection with the boundary, irrespective of whether we hit a part of the ball or a part of the boundary inside of the ball. And because the star-shaped boundary is always visible by construction, we're going to always be guaranteed that we have no interactions that occur like at multiple points. We're going to get a single point, can recurse there, and continue our walk. So altogether, this gives us the ingredients for the walk-on-stars algorithm for mixed Dirichlet and Neumann boundary conditions. And conceptually, this is very similar to walk-on spheres. So we start at a point x, and we compute the largest star-shaped region, which could either be a ball if the closest point is coming from the Dirichlet boundary, or it'll be a star-shaped region at this point x1. And then we just continue to sample points as we would in walk-on spheres until we reach the Dirichlet value, or the Dirichlet boundary, where we'll add a Dirichlet value to our estimate. And we can just repeat this walk procedure many times and take the average of all of these Dirichlet values, and this will give us the solution to a PDE with Neumann boundary conditions. So the key difference to walk-on spheres, as you can see in this picture, is that our random walks now reflect off of the Neumann parts of the boundary. So we're back to capturing the behavior that we wanted at the beginning of this section, but now we're doing it in a way where we preserve all the benefits of walk-on spheres. The final question is, how do we actually compute these star-shaped regions, which will allow us to take large steps? This turns out to be easy to answer as well. So rather than finding just the closest point on the boundary, as we do in walk-on spheres, we now find the closest silhouette point on the Neumann boundary, and then we'll take the minimum of these two distances to define a star-shaped region. Now, by closest silhouette point, I specifically mean like the point on the boundary where the normals will change from being front-facing to back-facing, or vice versa. Okay, now all of this might sound a little complicated, but we can actually compute the closest silhouette point very efficiently using the exact same boundary volume hierarchy that we already use for ray intersections and closest point interactions. The only thing we need to do is store a little extra information about the boundary normals, so we'll encode the orientation of the geometry inside of each node. So there's one caveat with using walk-on stars, which is that near concave parts of the boundary, the size of the star-shaped region will shrink to 0 because the distance to the closest silhouette point goes to 0. So in order to prevent walks from getting stuck on concave parts of the boundary, we have to impose a minimum epsilon on the size of the ball, and this will come with a little bit of a performance and bias trade-off, much like the epsilon shell in the Dirichlet boundary case. But it's important to note here that the size of the star-shaped region is typically much larger, even slightly away from the concave boundary. So in practice, we may have a small step that we take off of the Neumann boundary into the domain, but then immediately our step size will become large again. And additionally, we can use local curvature estimates so that we can actually set this epsilon value adaptively. And this should essentially allow for larger spheres and faster runtime performance as a result. So to recap, the final algorithm is actually very simple. We just check if we're near the Dirichlet boundary. If not, we find the closest point and the closest silhouette point, and then we shoot a ray at the corresponding star-shaped region, and that'll give us our next random walk location. And we just repeat this until eventually we reach the Dirichlet boundary, where we add that value to our total. And we just repeat this n times. So you'll notice that the only thing that's really changed from walk-on spheres is that we are essentially performing one extra geometric query when we find the closest silhouette point. Notice that walk-on stars will actually automatically turn back into walk-on spheres when there's no Neumann boundary. And that besides just the close resemblance to walk-on spheres, we still have preserved a lot of the simplicity in these algorithms in the implementation. So we actually have a step-by-step tutorial available for building this algorithm up from scratch, and you can do the entire thing in 150 lines of C++ without any external dependencies. And so you can find that tutorial at this link here. And in addition to this tutorial, we actually have a full reference implementation that has a number of additional features beyond those I've discussed, including treatment of non-zero Neumann boundary conditions, where you additionally will pick up an additional contribution with every reflection, and the treatment of pure Neumann problems where there's no Dirichlet boundary to terminate on, as well as the handling of open domains and double-sided boundary conditions, such as in this example where we're generating a diffusion curve image on really intricate geometry. And recently, we even generalized walk-on stars to also handle Robin boundary conditions. So while Dirichlet boundary conditions will prescribe fixed solution values, and Neumann conditions prescribe fixed normal derivatives, Robin boundary conditions will give us a linear combination of the solution and the normal derivatives. And Rohan will discuss this extension more in his Brownian motion section. So finally, walk-on stars immediately extends to Poisson equations, and we can also go and estimate spatial derivatives like the gradient. finally, we also stress tested this solver on a number of models with really complex geometry, just to show that the scalability actually holds up with these new queries that we add and the slight change to the algorithm. So here we have oxygen diffusion on a super detailed model of the lungs. And by solving a Laplace equation with mixed Neumann and Dirichlet boundary conditions, we can model this effect. Unlike a traditional grid-based solver, we don't have to solve the solution everywhere in the domain. We can actually just pick out slices where we want to analyze the concentration of oxygen. And if you go and think about what you'd have to do with an FEM solver in order to solve on this domain, you can see that you're going to run into one of two problems. Either if you limit the amount of time or memory that your meshing algorithm can take, you're going to end up with essentially your meshing process losing detail in the boundary geometry. Or if you let your meshing algorithm have more time in memory, it's going to take an extremely long time to actually get an accurate simulation-ready mesh. And this is really the big takeaway here. It doesn't matter how fast or accurate the FEM solver is, as long as the mesh generation is still slow or unreliable. Another example that's not from a math or an engineering textbook, but rather from a book on baking bread, essentially highlights that it would take an extraordinary effort to try to represent the intricate and highly variable patterns in a heat transfer model for baking bread. And we tried to take on this challenge in a toy model where we used walk-on stars to simulate how bread might brown under different toasting conditions. And we used a detailed CT scan of a piece of toast that had or has 4 million triangles. And the interesting thing here is that the Monte Carlo solver can actually provide a preview faster than going and running a real toaster. And so this gives you a chance to essentially see how your toast is going to turn out while you're waiting for it to toast. Here we also have a lizard that's sunning itself on a rock, where the Dirichlet boundary conditions provide the heat on the rock, and the Neumann conditions describe how much heat the lizard is going to absorb. And if we run walk on stars, we can make sure that the lizard isn't going to get too hot or too cold as it sits on this rock. So in this example, we used a polygonal mesh to represent the lizard and actually a signed distance function for the rock. So already we're mixing different types of geometry, and this is just naturally handled by performing queries over two different types of geometry. For the Dirichlet conditions, we also call a ray tracing algorithm just on demand wherever we need the instant radiant flux density. So we don't actually have to go and compute this ahead of time. We just run walk on stars, and when we reach the Dirichlet boundary, we perform a rendering procedure to compute the instant radiant flux. And really the key thing to take away from here is that it's super easy in this framework to mix and match not only the different geometric representations, but also the Monte Carlo algorithms, or even mixing and matching walk-on spheres potentially with non-Monte Carlo solvers. Now, finally, compared to other Monte Carlo algorithms like the walk-on boundary method, where rays intersect the boundary multiple times, we find that walk-on stars does much better, both in terms of variance and bias, especially as the boundaries become more reflecting. And this is really because in moving from the initial integral expression that we showed to this random walk procedure, we're very sure to make sure that the integrals are satisfying this property that Ioannis discussed much earlier, that the spectral norm of the operator is less than 1. So things aren't going to explode over time, they actually converge. And so just by changing the shape of the domain in our case to a star-shaped region instead of an arbitrary one, we're actually able to completely control the noise. We pick a particular type of star-shaped domain, but it's likely possible that you could use different subdomains to allow you to take even larger steps and maybe even reduce noise further. But the key point to stress here is that it's almost never sufficient to just throw the Monte Carlo hammer at the integration problem. You actually need to kind of take geometric insights and understand the integral you're solving and make sure that it's going to give you a stable recursive estimate. And we'll see another example later in this course during Sina's presentation where geometric insights actually become really crucial for solving these sorts of PDs in exterior domains. Now, of course, walk on stars has limitations similar to a ray tracer. One of those being that it can require some really long walks to find its way through narrow features in the geometry. So we only terminate when we reach the Dirichlet boundary, which is on the other side of this bottleneck. So we kind of have to hope that eventually our random walk will happen to go through this tiny tunnel. But with Monte Carlo methods, despite this limitation, there's always room to build more efficient estimators that can overcome these sorts of shortcomings. And we'll see some examples later in this course as well on how to overcome these problems, or at least make solving these problems more efficient. All right. And now Rohan will walk you through some of the connections of walk-on spheres to Brownian motion.
Okay, so up till now, we've described how to solve Laplace and Poisson equations by building Monte Carlo estimators for the boundary and mean value integrals. However, we can actually also describe these estimators through an entirely different lens of stochastic differential equations and Brownian motion in particular. In my opinion, this stochastic perspective actually really enriches walk-on spheres and walk-on stars, and it also helps us build practical intuition on how to generalize these algorithms to solve even larger classes of problems. So this starts with Kakutani's principle, which says that if we want to solve a Laplace equation with Dirichlet conditions at a point x, then we simulate realizations of a random process called Brownian motion to the boundary and compute the expected value of the boundary function g at the points where the random walks terminate. We do this by using standard Monte Carlo integration. Intuitively, Brownian motion is a collection of independent random increments where each increment is sampled from a normal distribution whose variance is given by a time parameter delta t. In the limit of smaller and smaller increments denoted by dwt, we then get a continuous random path described by Brownian motion. So Brownian motion is named after the Scottish botanist Robert Brown, who was the first to use a microscope to study the erratic movement of pollen in water in the 1800s. In the early 1900s, Einstein then related this random motion of Brownian particles to the solution of a heat equation and its steady-state counterpart, the Laplace equation. And then in 1923, Norbert Wiener provided a rigorous mathematical framework for Brownian motion. The random process he described is now formally known as a Wiener process, and it's a key concept in probability theory. So Brownian motion has found widespread use in many scientific applications, probably because it's the simplest mathematical model for events that change randomly over time. So it models thermal fluctuations in physics, the dynamics of reaction diffusion equations in chemistry, the volatility of stocks in financial engineering, and the uncertainty of unknown events in optimal control, such as the wind forces affecting an aircraft. As some of you may know, it's also the noise model of choice in machine learning for image synthesis algorithms based on diffusion models. Now, because of this universality of Brownian motion, people have naturally looked into ways to simulate Brownian motion. So the most obvious simulation scheme actually comes from the definition of Brownian motion itself. At any point wt1, simply add an increment sampled from a normal distribution to get the next walk location wt2. This numerical integration scheme is called Euler-Maruyama, and it's basically an equivalent of forward Euler for simulating Brownian motion in unbounded domains. OK, but what about geometric domains that are bounded? So here we face a number of challenges. If we take time steps that are too small, then we can end up simulating Brownian motion accurately, but we get long compute times. If we instead take time steps that are large, then we have shorter compute times, but large bias from discretizing our random walks. And this bias actually accumulates with every step of the random walk, even if we carefully choose our time parameter. My cursor? Here we go. OK. In bounded domains, we also have additional bias from needing to truncate the final step of the walk, which can easily end up jumping from one part of the domain into another, since a normal distribution has infinite extent. So at this point, it really shouldn't come as a surprise that we can overcome these efficiency and bias issues by simulating Brownian motion using walk-on spheres. So here we observe that a random walk starting at x is actually equally likely to exit through all points on the sphere centered at x. because of this rotational symmetry of Brownian motion. And so if we uniformly sample a sphere, then there's no discretization error at all. Now, Brownian motion isn't the only rotationally symmetric random process, but its exit distribution is uniform for a sphere of any size, whereas other symmetric processes typically impose additional constraints on the sphere radius. OK, so then if we restrict our domain to a ball, this implies that Kakutani's principle is actually equivalent to the mean value property of harmonic functions. And we can basically think of walk-on spheres as an unbiased acceleration strategy for simulating Brownian motion in bounded domains. In fact, this property of walk-on spheres as a simulator for Brownian motion can make it more broadly useful in application domains that require sampling of white noise as well. With a Poisson equation, we have an additional source term f. So here, the stochastic picture is that a Brownian random walk now picks up a background contribution f as it wanders through the domain. We can now, again, restrict the domain to be a ball and ask where, on average, inside the ball, a random walk spends its time. We then eventually recover a distribution that's equivalent to the Green's function of the ball, which is known in closed form. So our final integral expression now multiplies the Green's function with the source term inside the ball. More generally, we can leverage this duality between the stochastic and integral perspectives to solve a much larger class of differential equations, where our general recipe is to first find a stochastic representation for our PDE over an arbitrary domain, then to convert it into an equivalent mean value relation restricted over a ball, which we finally estimate recursively using Monte Carlo. In all cases, this whole derivation can actually be explained without the stochastic representation. But the stochastic perspective actually provides a lot of useful insights, which can be hard to come by if we only look at the integral equations. So as a concrete example, the insight of performing reflections on the Neumann boundary with walk-on stars came from the literature on stochastic differential equations, where Brownian motion is absorbed on the Dirichlet boundary and reflected off the Neumann boundary. On a 1D half-line, reflected Brownian motion is formally defined as the absolute value of ordinary Brownian motion. This definition extends to polyhedral domains as well, where Brownian motion is reflected back into the domain across any face it crosses. So we can simulate this reflected Brownian motion using standard numerical integration schemes, such as Euler-Maruyama. But this tends to produce extremely biased results in bounded domains. And it's also very slow, even in domains with simple geometry because of small step sizes. In comparison, walk-on stars takes large steps and introduces negligible bias. The stochastic perspective also helps us to extend walk-on stars to Robin boundary conditions, which are basically a linear combination of Dirichlet and Neumann conditions controlled by this coefficient mu. So at the extremes, when mu equals 0, we get purely reflecting Neumann conditions, while mu equals infinity gives purely absorbing Dirichlet conditions. And then we can interpolate between these two extremes by increasing the Robin coefficient mu. We actually used these Robin boundary conditions in the Mars rover example shown earlier because they describe surfaces that are neither perfectly reflecting, like an ideal insulator, nor perfectly absorbing, like a black body. And in general, these boundary conditions provide a more realistic description of physical materials. Also, compared to Neumann conditions, estimators for Robin problems are more efficient because from a stochastic perspective, they require simulation of partially reflected Brownian motion, which has some non-zero probability of being absorbed on the boundary. So we use this insight to develop a version of walk-on stars that also has a non-zero probability of termination on the Robin boundary, which helps to improve the efficiency of our estimator because of shorter walk lengths. I won't go into the details here, but at a high level, we observe that the radius of a star-shaped region should be smaller than the distance to the closest silhouette point on the Neumann boundary, but also larger than the distance to the closest point on the Dirichlet boundary, since intuitively, Robin conditions interpolate between Dirichlet and Neumann values. So this choice of a star-shaped radius then introduces what we call a reflectance function on the Robin boundary, whose value is bounded between 0 and 1. So it naturally gives us a probability with which random walks should be absorbed on the boundary. OK, so now I'll briefly describe one other scenario where I think the stochastic perspective really comes in handy. So real-world physical systems often exhibit complex spatial variations that affect thermal and electrical conductivity, elastic response, and even the flow of groundwater. It turns out that we can model such fine-scale structures using generalizations of the same Laplace and Poisson equations we've described up till now, but with spatially varying coefficients. So in particular, we already know that the Laplace equation describes the steady-state temperature inside a domain if the temperature is set to some given function on the boundary. Adding a source term f yields a Poisson equation, where f describes the background temperature. We can then augment this equation to also control the rate of heat diffusion by replacing the Laplacian with an operator grad of alpha grad u. So physically, the scalar coefficient alpha here controls how quickly heat diffuses into different parts of the domain. Another generalization is to add a transport term, omega grad u, which indicates that heat is now pushed along some vector field omega. So imagine a flowing river which mixes hot water into cold water until it reaches a steady state. And finally, the absorption term, sigma u, acts like a background medium that absorbs heat. So think of a heat sink or a cold engine block. Now, there are lots of other terms we could add to a PDE, but these already get us pretty far. So the question now is, how do we solve these variable coefficient equations? For some of these more advanced equations, we actually don't even have mean value integrals readily available. But what we do have is a stochastic representation that uses generalizations of Brownian motion. So we already know that Brownian motion uses independent random increments sampled from a normal distribution. Adding a velocity term, omega dt, to our Brownian motion then gives us a diffusion process, which we can think of as either a random walk with drift or some deterministic particles with noise. We can also modulate the strength of this random motion using a scalar function alpha. So as alpha increases, things heat up, and particles move faster. And finally, random walks can also be absorbed into a background medium, where the coefficient sigma controls the strength of absorption. Sigma actually doesn't show up in the stochastic differential equation, but will be incorporated in just a moment. Now, it's no coincidence that we use the same symbols, alpha, omega, and sigma, for both our PDEs and our random processes. These perspectives are linked together by the Feynman-Katz formula, which gives the solution to our variable coefficient PDEs as an expectation over many random walks sampled from a general diffusion process. So unlike classical integral expressions, this formula actually handles spatially varying coefficients. Now, what's interesting is that the Feynman-Katz formula actually looks a lot like the volume rendering equation, which in computer graphics describes the radiance along a ray in a heterogeneous medium that absorbs, scatters, and emits radiation, like a cloud or a puff of smoke. But if for a second we just put aside the physical meaning of these symbols, then structurally, the main difference between the Feynman-Katz formula and the VRE is that one requires simulation of Brownian random walks, while the other provides the radiance along a ray. So the structural connection is really interesting, because if there's a way to exploit it, then PDEs can suddenly benefit from decades' worth of volume rendering research. So the key observation behind our approach is that even though walk-on spheres cannot directly handle PDEs with variable coefficients, it can still solve problems with spatially varying source terms. So we therefore apply a series of transformations, some of which are identical to those in volume rendering, to convert our original variable coefficient PDE into a constant coefficient screen Poisson equation with a recursive source term. I, again, won't go into the details behind these transformations, but notice that the source term now depends on the variable coefficients alpha, omega, and sigma, as well as the solution u. So from an FEM perspective, it might actually feel like we haven't done anything useful. We just shuffled all the hard stuff to the other side of the equal sign. But from the Monte Carlo perspective, we actually now have a way forward because we've essentially re-expressed our diffusion process for variable coefficient problems purely in terms of Brownian motion, which we know can be simulated using walk-on spheres. So if we take a closer look at the corresponding integral expression for our transform PDE, it says we now have to recursively estimate both the source and boundary integrals. So again, I won't go into the details here, but at a high level, we achieve this by designing variants of walk-on spheres for variable coefficients that are heavily inspired by volume rendering algorithms such as delta tracking. These modified random algorithms, random walk algorithms, then allow us to solve differential equations with variable material coefficients in scenes with extremely complex geometry without any pre-processing or homogenization. So for instance, from this view alone, the boundary meshes used to represent these black body emitters have 600 million vertices. With even just a single object in this scene, we find that FEM can't resolve either the original geometry or the material coefficients or the PDE solution. Now, adaptive mesh refinement fixes this, but notice we now have 8.5 million tetrahedra, and we needed 2.5 hours of meshing time to resolve the aliasing artifacts. And that's just on a single model in this scene. Now, some conventional PDE solvers, such as the boundary element method, famously don't need a mesh of the domain at all. But it's worth pointing out that unlike walk-on spheres or FEM, these solvers cannot directly handle problems with source terms or spatially varying coefficients. To handle these terms, BEM would have to be coupled with a secondary solver that requires volumetric meshing or sampling. Unlike BEM, the Monte Carlo approach is robust to aliasing artifacts because it's tessellation independent, and it doesn't have to deal with dense singular matrices either. OK, so I hope this gives you some sense of the type of PDEs that we're able to solve with walk-on spheres today. But I actually think it's still too early to say exactly what classes of equations one can hope to solve if we keep building. So for instance, there's a whole zoo of random processes in the SDE literature that's related to different types of PDEs, including certain nonlinear diffusive equations. Beyond the Poisson equation, boundary integrals are also known for the heat, Helmholtz, wave, and biharmonic equations, as well as linear elasticity. And in many cases, more complex nonlinear PDEs are often solved by decomposing them into a series of Poisson equations. But it remains an open question whether we can actually solve the equations listed on this slide using walk-on spheres. So towards the end of this course, I'll discuss some of the challenges we've faced in trying to move beyond diffusive problems. OK, so let's take a couple of minutes. Let's take a short break here. And we'll get the next set of invited speakers set up, who will cover more advanced topics such as variance reduction, differentiable solvers, handling exterior problems, and hybrid neural and Monte Carlo techniques. So please stick around.
And we'll take questions.
Sure. Yeah. No, actually, I think we should keep. So if you want to get set up, I think yeah. I'm just keeping track of time. Yeah. Yes. Yeah.
If you guys could, hello? If you guys could head back to your seats, we'll start in about a minute. All right, welcome back. I'm Wojtek. I'll be talking about how to make these algorithms a bit more smart about where they spend their computation and hopefully make them faster along the way. Okay, so if you recall, we posed these methods sort of in direct analogy to path tracing and rendering. That's my area, so I'm really comfortable with this space. And I'll look sort of at the class of techniques that rendering has used to try to make rendering faster and see if we can apply those also to walk-on spheres. So there's been decades of research on this in rendering to make path tracing more efficient. One of the things rendering folks have realized is that when you look at illumination on a surface, it's really complicated to compute. You have to trace lots of rays, but it tends to vary slowly across the surface. And so while we can compute all the pixels in parallel, it seems a little wasteful to have to recompute everything that ends up giving you a color that's very similar to the pixel next to it. And so one approach to accelerate this is to simply not compute it from scratch at each pixel. So instead, you could use the expensive Monte Carlo calculation only at a sparse set of locations in the scene, and then try to interpolate as much as possible everywhere else, we're assuming that interpolation will be faster. So this is an algorithm called radiance caching all the way back from the 80s, developed by Greg Ward, which was quite popular for a couple decades. And even in Rohan and Keenan's original walk-on spheres paper, you can already start applying this method. So this is a simple diffusion curves image reference solution where you're computing the solution at every pixel. But instead of evaluating it densely, you can simply evaluate it at a sparse set of locations that I'm showing here, and now interpolate everywhere in between. So this is only evaluating at about 1 out of every 100 pixels in the image. While there is a difference to the original, you're losing some detail, it's already quite close. And you can get even better by just adaptively placing where you expect the function, the solution to vary more quickly, place more evaluations at those locations, so sort of clump it around the curves here, and that improves things even further. Again, only evaluating at every 1 out of 100 pixels. So that's sort of in direct analogy to this irradiance caching algorithm. There's lots and lots of variants of this basic idea where you'd like to reuse information across your evaluation points. Another category of that is in rendering, we notice like our images are noisy because we're using Monte Carlo. And so we could just run a denoiser on the final outcome. Right? And so generally the way this works is for each pixel in your noisy image, you look at a local neighborhood and perform some sort of intelligent average of the pixel values, maybe using some auxiliary information about maybe the normals and other things like this, to then clean up the image in the end. And this works remarkably well, and I would argue it's actually one of the main reasons that the movie industry was able to shift over to Monte Carlo methods over the last decade or so, because it really removed that long tail of convergence from Monte Carlo. And now you're starting to see the same thing happening in video games with GPUs being able to ray trace and path trace. Unfortunately, you only have the budget to trace a few razor paths per pixel. And so if you try to do this at real-time rates, you get this garbage that's on the left over here. But then there's techniques like Restir from a few years ago that essentially try to reuse samples intelligently across pixels to amortize that cost. And now this is starting to be used in video games in real-time settings as well. And so basically we'd like to try to reuse this. The reason we can get speedups is because there's typically going to be millions of these pixels or evaluation locations that we'll be considering. And if we can reuse computation across those, we have the possibility of amortizing that computation and massively improving speed. And so what I'll discuss is 3 techniques that were developed over the last few years. And in large part, they borrow from techniques in rendering and then apply those in analogy to the walk-on spheres algorithm. So I'll start with this method called mean value caching, which was developed just a couple years ago. And so just like in rendering, with walk-on spheres, our estimates tend to be noisy if we only use a few walks. And the reason it has this particular kind of noise is because we tend to estimate the values independently per pixel. So you have independent noise from pixel to pixel. And we can clean this up just by taking more and more of these walks. We compute these walks by expanding the largest sphere at each evaluation location. And then by taking more of the walks, we can get a cleaner image. Now, if we look at the algorithm, the reason we were using the largest circle was because that gets us as close as possible to the boundary. But there's nothing preventing us from using smaller radii, right? We could have used any radius smaller than the bounded radius within this domain. Basically, all radii within that disk. And so really, any radius within this disk is valid. And so what this paper did is they realized that, well, instead of posing a mean value property around the boundary, you could equally well pose sort of a volumetric mean value property. So if you average the values within a disk instead of on the boundary of that disk, you're also able to pose that and relate it to the solution in the middle. Now, this doesn't seem immediately useful. Like, why would we sample within a disk if all we have to do is sample along the boundary? That seems like a simpler problem. The reason this gets useful is that now these disks around neighboring pixels overlap, and we can share computation across them. So what you can do is compute a low-quality estimate, maybe one random walk per pixel, and then you go through all of your pixels again, and instead of tracing more walks, you average the estimates from all the nearby pixels that fall within that disk. Right? And so now you're able to not just use that one walk within your pixel, but the potentially hundreds or thousands of walks from neighboring pixels and massively amortize the computation. And you can, in a sense, think of this as a denoising filter. It's averaging colors from nearby pixels, but it's done in a way that's aware of the properties of the PDE by using this volumetric mean value property. In fact, you can do this multiple times. So after one pass, you can do this reuse pass again and again, and that allows information to propagate over larger regions of the domain. Now, this isn't perfect, but what we did is we started with an image with one walk per pixel, and without tracing any more walks, get the image on the right that's much smoother. Okay, so the second technique that I wanted to talk about is boundary value caching from Bailey and Rohan and others here. And this one takes a more direct inspiration from techniques in rendering, so-called virtual point light methods. These methods essentially accelerate rendering by depositing radiance values within the scene first, and then at each shade point during rendering, they can quickly figure out the contribution from each of these so-called virtual point lights to each shade point. And so in our context, we'll consider the Laplace equation with Dirichlet boundary conditions. And we can write the solution to this PDE with this boundary integral equation that we saw before. But unlike walk-on spheres, we'll now let the G function be the free space Green's function over all of space. And it turns out that this is known analytically in closed form. And so what this equation really says is that if we know both the value and the directional derivative of the solution on the boundary, then we can compute the solution U everywhere within the domain. Now, to evaluate this, we'll simply form a Monte Carlo estimator. We'll uniformly place samples along the boundary. And we can then directly use the known Dirichlet data at all the points on the boundary. But we'll need to compute or estimate this normal derivative. And we can just do that by tracing a walk. So instead of tracing walks from within the domain, we'll trace them starting on the boundary. And so the interesting part here is now, once we have estimates of the derivatives, we can then propagate these values to any evaluation point within the domain. And nothing stops us from using the same set of Monte Carlo samples along the domain for every evaluation point. So they can now share this information. And so this likewise gives you these smoother results. You no longer have this per pixel variation in the estimate because they share random values. And so you get smoother results. The sort of characteristics of your error end up changing from being independent to correlated. Okay. So now one downside of this technique is that since we're simply reusing the cache points, you can suffer from artifacts near the boundary. And this is because the Green's function and the Poisson kernel, they're actually weakly singular. So they have these big spikes at the center. And you can see these as these little blotches near the boundary. But rendering folks have been looking at this problem for many years, and they have techniques to mitigate this, and you can apply similar ideas also with this technique in the walk-on spheres domain. Okay, so the final reuse technique I'll mention is one that takes this analogy to rendering even further, this reverse and bidirectional walks. So as I mentioned before, one common approach for rendering is called path tracing, which traces paths starting at the camera. They randomly bounce around the scene until they hit a light source, right? Similar to what we're doing with walk-on spheres. But in rendering, there's alternate approaches. One of those is, well, let's just trace light in direct analogy to nature. We'll have it leave light sources, scatter around in a scene, and hopefully hit a sensor at some point. So a natural question is, could we create this sort of reverse type of estimator also for walk-on spheres? It turns out that they have complementary benefits for rendering. Maybe we can find similar complementary benefits for walk-on spheres. So the key insight is that we can actually write a mean value equation for the Green's function of the domain. Right? So we've been looking at Green's functions for balls. These are known analytically. For your general domain, you don't know this analytically, but we can form an integral equation that estimates this Green's function. And a fundamental property of this Green's function is that it's symmetric. So I can swap the parameters x and z, and I should get the same result. And what that means is I can create another expression, another integral equation that has basically swapped these x and z. And what this tells me is that I can, if I now estimate the top equation using Monte Carlo, it'll give us our standard walk-on spheres algorithm. It's a random walk starting at an evaluation point. But if I start with the bottom equation, it will form a random walk that starts at sources and then hunts around into space and tries to find evaluation points. And so here's what that looks like. So if we just have a simple Poisson equation, we can start walks now from sources instead of from each pixel. And we know exactly where the sources are strong, so we can directly sample from our source function. And now each step of the walk, we can actually splat the solution to lots of pixels simultaneously using the Green's function for the ball. And then this walk continues until it hits the boundary. Right? That's just one walk. And then to improve quality, you just generate many walks starting from your sources, and then this will converge as you have many of them. So here's a comparison for a simple Poisson problem. We have some source terms. This is forward walk-on spheres where the estimate is independent per pixel. And then this is what you would get if you use this reverse walk, where now the information is shared across multiple pixels. So here, you can also extend this to boundary value problems, where now instead of having a source function, you have values along the boundary. The walks in this case now start on the boundary instead of within the domain. And unlike in the forward case, if you recall, if you had boundary data that's really concentrated, your random walk, it would walk around randomly and hope to hit the bright parts of the boundary. Here we know the boundary function, so we can start these walks directly from the bright parts of the boundary function. And so it's a form of importance sampling. And then because we're also sharing computation across pixels, we can reduce a lot of this high frequency noise. Okay, so there's actually another class of techniques in rendering that go beyond this. They trace both from the light source and from the camera and then try to connect in between. We can do something similar for walk-on spheres, so we can do a reverse walk. And now instead of directly looking up these estimates within these disks at some location, we can decide, I'm going to take one or more steps in the forward direction. And what that does is it essentially smooths out the solution. If you have too few of these walks in the reverse direction, you can take some walks in the forward direction to reduce artifacts. And this is a common technique in rendering also. It's often called the final gather pass. And so here's a simple diffusion curves image with this ladybug. And if you only use a few of these random walks, reverse walks, you get these artifacts in the reconstruction. And then just by taking a couple steps in the forward direction, you can smooth those out in very little extra cost. Okay, so that's it. I just wanted to mention these techniques are really the tip of the iceberg. People have started looking at analogies between rendering and these walk-on spheres methods, but there's really lots and lots of other techniques you can start to pull from within rendering as well as other domains. Okay, so I'll hand it off to the next speaker.
Okay, so yeah, in the next little session, I'll talk about a different type of solvers, which are differentiable solvers, and their uses for solving a few inverse problems. So as you have seen in the previous talks, when we talk about a PDE solver, we mainly talk about a so-called forward solver, where we take the PDE parameters, as shown on the left, and perform a solve to get the solution of the PDE as the one shown on the right. So as you have seen in the earlier part of this course, following similar ideas as like path tracing and forward rendering, we now have Monte Carlo solutions for PDEs. That enjoys a lot of advantages offered by Monte Carlo, for example, not having to do meshing, etc. However, very often in many applications, instead of doing just a forward solve, we want to solve certain inverse problems. So in this case, what we have is either a solution of the PDE as some sort of a measurement, or a loss of the solution is kind of that quantifies how good the solution is. For example, you may want the temperature distribution to be uniform. You may want like the volume of a domain to be minimized, constrained by a certain PDE. So now in this case, what we want to infer would be the PDE parameters, including the shape of the domain, etc., given its solution or given a kind of a metric of that solution. So these are what we call inverse PDE problems. As I just mentioned, there are a lot of applications related to this type of PDE constrained design. So that's why we kind of, to some extent, solving inverse problems is kind of why we want to have forward solves in the first place. And very often, of course, these inverse problems are challenging. So instead of kind of directly infer the PDE parameters, we often formulate these problems as so-called analysis by synthesis optimizations. In this case, the goal is to minimize the loss, as we can see here, the loss function, which is considered given. We want to find the same parameters so that the loss is minimized. And just like in many other literature in computer vision and machine learning, we solve an optimization often using gradient-based methods. Right? We start from some initialization and iteratively update in this case, PDE parameters until the convergence is reached. And of course, if we apply the chain rule to the gradient of the loss, we get something like this, where we can see we need the derivative of the solution with respect to certain PDE parameters. So that's why we want, say, differentiable PDE solvers. So to summarize, Forward PDE solvers, you can consider it as a map from PDE parameters, including the domain shape, to its solution. On the other hand, the differentiable PDE solver focuses on estimating the derivative of the PDE solution. Okay. So now let's talk a little more about differentiable PDE solvers. As I just mentioned, here we can see an example. On the left, I visualize the solution of a Poisson's equation on a pretty complex domain. It's kind of a wired bunny domain. On the right, we visualize the derivative of the solution, in this case with respect to the translation of the whole object. So it's kind of a shape derivative in this case. So a differentiable PDE solver focuses on estimating the right side, basically. So now, of course, the question is how we do this. Fortunately, compared to other differentiable tasks like differentiable rendering, to some extent, solving relatively simple PDEs like the Poisson's equation in a differentiable way is kind of a simpler task because it largely boils down to another forward solve to some extent. So now let me explain what it means. So here we show a ordinary Poisson equation. So we know the Laplacian of this function in the interior of some domain, and we know, again, in this case, the Dirichlet condition on the boundary. So in a relatively simple case, when we differentiate with respect to some parameter controlling either the Dirichlet condition G or the source function f, but not the domain, we can do this by essentially differentiating both sides of the PDE. So we get essentially another, which we call a differential PDE, right? Where this u dot basically means the derivative of u. That's what we want to solve for. We basically get another pretty much Poisson's equation. And in this case, as long as we can efficiently differentiate the source function as well as the boundary condition function, very good. So conceptually, this is simple, right? We differentiate f and g, and we do basically another forward solve, and we'll get what we want. Of course, in practice, to do it efficiently, to, for example, avoid automatic differentiation, to run out of memory, and so on, precautions still needs to be taken. For example, Ioannis et al. Developed a method very similar to path replay backpropagation in differential rendering to make this differentiation process more efficient. But unfortunately, I won't be able to go over some of the details here. So that's kind of how we handle the conceptually simpler case when we differentiate with respect to the source function and the boundary condition. So you may wonder, what if we want to change the shape of the domain? Fortunately, this can be done as well using largely a forward solve. So now let's look at a simpler case where we handle a Laplace's equation. Poisson equation can be handled in a similar fashion, but here, to keep things simpler, I'll focus on Laplace equation here. So again, we take the ordinary Laplace equation, and it can be shown that if we differentiate with respect to the shape of the domain, the differential PDE looks like this. So in this case, the Vn is the so-called normal velocity of the boundary, because now we are changing the shape. So Vn captures basically the change rate of the domain boundary with respect to the parameter that we're differentiating with respect to. And here we also need to know the normal derivative of the Dirichlet function, which is known, and also the normal derivative of the solution, which I will talk about later. But at a high level, as we can see here, the derivative u dot still can be solved, mostly using forward Walkan spheres, because again, it's the solution of the differential Laplace's equation here. Okay. So of course, in this, we now focus on Monte Carlo solutions for all this forward solve. So you may wonder, what about the noise? Right? Monte Carlo solutions are noisy, so if we use Monte Carlo to estimate the derivative of the solution, it's going to be noisy as well. That's going to cause the estimated gradient of the loss to be noisy. Fortunately, this, at least at a high level, isn't a problem because mathematically speaking, stochastic gradient-based methods, including stochastic gradient descent, and to some extent ANOM as well, is guaranteed to converge so long as the estimated gradient is unbiased. In addition, the added variance sometimes can even benefit the optimization by avoiding local minimum. And in fact, this is exactly how quite a few existing inverse rendering pipelines work. They use noisy renderings and noisy differentiable renderings to solve inverse rendering problems. So here we want to emphasize that the same basically argument works for solving inverse PDE problems as well. Okay. So next, let me briefly talk about estimating normal derivatives. In this case, we focus on estimating normal derivatives on Dirichlet boundaries because those are where the normal derivatives are unknown. They are known at Neumann boundaries, right? So this is the slide I just showed. So here we want to say that, again, if we think about at the Dirichlet boundary, this normal derivative is unknown. So the question is, okay, how we can estimate it. This is, in fact, a non-trivial problem. One method used by, for example, Bailey in earlier work is to just use finite difference, right? So we can say that, well, if I add some point x on the boundary and we want to know the normal derivative, we can basically shift the point x a little bit inward to get the point x prime, and then calculate the difference between the two. At x, we know the solution is just given by the Dirichlet condition, right? And then we estimate this finite difference, and of course, this solution u at x prime can be estimated using the forward Walk-on spheres. So this works adequately, but there are a few challenges, which is, of course, we have to determine how big this spacing L is. If we use a very large spacing, we can suffer from high bias. If we use a very small spacing, it can basically increase the variance of this u of x prime estimate quite a lot. So that can be a challenge. So to address this, we introduced a different method recently, which uses the so-called off-centered kernels. So if we, as like Wojtek and others discussed earlier, if we use the BIE formulation, we have the freedom, the flexibility to choose different domains. So here we use a domain that looks like this. So it's a domain that's kind of tangent to the point x at the boundary, and domain is still a sphere. Okay, so this we call it a off-centered ball. So fortunately, this kernel has kind of closed forms, or at least can be approximated using closed forms. And the idea here is that if we want to take the normal derivative, we can actually estimate the normal derivative of the off-centered Poisson kernel. Of course, this is with respect to x moving along the normal, so that's how it's defined. So we can estimate this normal derivative using this based on this off-centered formulation. Something like this. By sampling, of course, we can do this using Monte Carlo by sampling y and again, estimate uy recursively. However, there are a few challenges, which is about singularity, because we already know that very often the off-centered Poisson kernel itself is already weakly singular. If we take another derivative, it makes it even more singular. So that's the problem. So again, if we look at this, the issue is that when y approaches x, this integrand approaches infinity. And again, it can become even hypersingular in certain cases. So easy sampling tricks won't address this problem. However, here we found a very interesting technique, which is control variant. But unlike any other control variant in rendering, that kind of addresses this. So we noted this property. If we integrate this normal derivative of the Poisson kernel over the surface of the off-centered ball, it's 0. So if we multiply a constant to this, it's still 0. It's still 0. And now we use this 0 as a control variant. So if we subtract 0 from the equation above, we get this thing below. Okay, it's because we subtract 0, nothing changes. However, the interesting property here is that now in the integrand, we have a term that approaches 0 when y approaches x, because that's when we get the Differential condition. And we can show that in this case, the integrand actually converges when y approaches x. So we kind of magically remove a infinity by subtracting 0 on both sides of this relation. So that, yeah, this is the interesting type of control variant, right, which is 0. And of course, to further improve the efficiency, we show that by doing some sort of anesthetic sampling, in this case symmetric along the line connecting point X and the center of this off-centered ball, we can achieve even better convergence. So here is a little kind of ablation study, as we can see if things diverge, as we can see on the left. Using more samples doesn't really help because we get infinity, essentially. That means infinite variance, pretty much. If we apply this subtracting 0 trick on both sides, we get a lot better convergence. So finally, the algorithm looks for estimating normal derivatives, looks like this. So first, again, this is the full algorithm, I'm sorry. When we reach y, then we need the normal derivative at y. So we start this off-centered sphere trick. And then by doing anesthetic sampling, we sample 2 symmetric passes from y to get the normal derivative at y. And that kind of completes the shape derivative estimation of the solution field. Okay. So now I'm just going to very quickly show a few inverse examples. So here, this is an example from the work by Ioannis et al. As we can see that using automatic differentiation and the efficient estimator, we can match the reference solution. In this case, we are optimizing the source function. Right? We can match, starting from pretty much a constant initialization, we can match the source quite easily using estimated derivatives. And in this case, we show an example from the work by Yu et al., where we optimize the shape of a diffusion curve. And we can see, again, by using correct shape derivatives, we can do this type of shape optimizations quite easily. And finally, this is a thermal design example from the work by Bailey and others. So in this case, what's being optimized is the wire geometry of basically a heating element over here. And we want the toast to have this certain ham text on it. And also by using the shape derivatives, the geometries of these wires can be optimized. So as you can see, initialized with just some straight wires, we get quite complicated shapes that achieves this pattern on the toast. Okay, so again, these are all pretty proof of concept examples. In the future, I think it's quite worthwhile to explore this type of techniques in real world applications. Okay, thank you.
Hello? Okay. Yeah, so I'm Sina Nabizadeh, and I'll be talking about this paper we had a few SIGGRAPHs ago in 2021, using Kelvin transforms for simulations that happen not on the interior of shapes, but actually on the infinite domain in the exterior of the shapes we're interested in. So for example, in geometry processing, we're interested in vector field design, and it's been mainly limited to bounded interior domains like this one. But using Kelvin transform, we're no longer limited to this, and we can actually solve for the entire infinite exterior domain. Specifically for Monte Carlo geometry processing, we saw today that the solution to the PDE, for example, this Laplace or Poisson PDEs, are random walks that start somewhere in the middle, and they end up on the surface. But if we're interested in a problem that's on the exterior, it's infinite domain, the random walks actually seldom terminate on the surfaces. So instead, we use this method called the Russian roulette, which aims to stochastically terminate these walks. So we end up with all walks that are actually finite. But this is not a perfect solution. So consider this equipotential crab, which is put next to this oppositely charged point source. This is a Poisson problem. And if we're asked to extend the potential to the surrounding space, say we visualize it on a flat plane, we get the following results using the Russian roulette method. We get a small hint of where the point source is or should be, but in general, the solution is very noisy, and it has a very slow convergence. And our only solution is really just to increase the samples and hope that we get a better results. But that's very computationally intensive. So we like to solve this problem not by using the Russian roulette method, but instead using the geometry that's inherent in our PDEs. And it turns out that if we use such methods, we greatly reduce the variance, as you can see flipping between these two. So, okay, how do we do this? So our work was motivated by this classical Kelvin transformation by Lord Kelvin from 1845. And it basically comes down to that Lord Kelvin was studying electrostatics and introduced what we now know as the method of images, which is to solve point charges near conductors in the shape of spheres or planes, which is also a sphere with infinite radius. And at the heart of this method was this clever transformation, which is called inversion in a sphere. It's a special kind of conformal map. These maps preserve angles, and crucially, they preserve harmonic functions, which are solutions to the Laplace PDE. The relation between like the original solution, u of x, and the one that's transformed, v of y, it naturally breaks into two steps. We have a coordinate mapping step, which is an inversion, and the second one is a scaling or a factorization, which happens post-transformation. This was the method that Kelvin used, mainly for Laplace problems. So this is going to be our guiding principle moving forward. So consider this coordinate mapping scheme, which is this inversion, which we achieve by simply dividing by the square root of distance to the origin. So once we're in the inverted domain, we can set up our favorite discretization or even solve it using Monte Carlo geometry processing and invert back to the original domain using the same inversion scheme. Beyond inverting the actual coordinates, we can use this inversion scheme to invert solutions from the inverted domain to the bounded domain and vice versa. However, this inversion comes at a significant price, actually this singularity point. This is going to cause problems when we're solving our PDEs, and we'd like to remove this singularity if it's possible. So consider these two problems, Poisson problem, which we've been mainly talking about, and also Helmholtz PDE. Well, it turns out that their behavior as they extend to infinity for the Poisson problem is that it decays inversely with distance. And also in the Helmholtz case additionally has an oscillatory behavior. If you apply coordinate mapping to these sort of the behaviors as they approach infinity, we see that they come up with sort of a problem at the center. For the Poisson problem, it comes up with the non-differentiability at the origin. And for the Helmholtz case, it similarly comes up with this infinite frequency that no discretization is able to actually resolve. So ideally, we would like to remove these singularities. As it turns out that we can actually remove them by using a simple decomposition to two functions. One function g that captures the analytic behavior and captures out the singularity, and one free of any singularity, a smooth function which we can actually solve for now. And this smooth function, we can solve it with our favorite solver here, I guess, is the Monte Carlo geometry processing methods. To recap, what I mean is that, let's say we're interested in solving this problem in the exterior of the bunny. So we first do a coordinate mapping inversion. We get a bounded problem. We know we're going to have a singularity problem, so we factor that out using this analytical function g. We solve for the remaining smooth function v, and all we have to do after is multiply them back and use another inversion scheme to get all the solution surrounding the bunny, the infinite solution. So mathematically, let's look at the Poisson problem. Let's say we're interested in this Poisson problem in the infinite domain. So simple coordinate mapping, we can get the PDE in the inverted domain. And we see that there's actually a problem if we just apply the symbol inversion. We get that y over y squared, the distance to the origin. And we wouldn't be able to actually solve for this PDE. Like we've seen today, this is not the kind of PDE we're comfortable in solving. So what we instead do is that we note that the analytical function is actually decaying with 1 over distance, which is going to be this sort of sharp function y in the inverted domain. We factor that out, and the remaining function is v. So we see that actually the PDE that remains is actually another Poisson problem with a different right-hand side. We're comfortable in solving this one now, and we see that that 1 over y squared doesn't show up anymore. So actually, to note is that to use our method, this Kelvin transform, what you really need is the inversion method and a method of factorization, some method that captures the singularities out of the problem. And if you look at the sort of pseudocode of this problem, you see that all you really need is a method to solve the interior Poisson problem. And the rest of the steps are just simple arithmetics. So looking at some results, going back to the Monte Carlo geometry processing-based methods, let's say we have this Laplace problem with a Dirichlet boundary condition. And we're interested in solving it. So what we do is the regular walk on spheres for the interior problem. And this is written as its expectation value. But for the exterior problems, we have this Russian roulette method where we're actually terminating walks with some probability lambda. And for the walks that do end up on the surface, we will be adjusting them by this 1 over lambda to the power of number of steps in our path or walk, which is inherently just increasing the variance of our problem. Now, if you compare Russian roulette with our method, which is happening as a random walk in the inverted domain, you see that in our method, all of the walks actually terminate on the surface, 100% of them. And for fun of it, if you actually invert these walks back to the original domain, you see that they show up as these walk on these arcs. That it's because really that the straight lines in the inverted domain become circles because of this conformal map. So now in 3D, if you want to visualize this, is that let's say we're interested in the exterior of this 3D bunny, and we run the Russian roulette method, and you can see that only 8 of the 100 walks actually end up on the surface. Now, if you use Kelvin transform, run the same thing, you see these little circular paths, but 100% of them actually end up on the surface, as we expect. So we have this protein molecule, and we're interested to see the sort of the potential around it. So we establish an equipotential map first, and we ask what is the potential surrounding it, let's say on this plane. And again, with Russian roulette, we get a very noisy method result. And with our method, we get less noise. And if we plot it just to confirm our results, you can see that there's a large gap introduced as this variance reduction using Kelvin transform for exterior problems. Now, I mean, we can use it for quite interesting problems. Let's say we're given this data from NASA with the magnetic flux on the sun, and we're asked to like extend the magnetic field to the surrounding. Usually people use domain truncation, which is like they cut off the domain, set some values there, and they solve for the problem. But that really disturbs the results. So using our method, we can actually solve for the entire infinite domain. Like we can pick any point we're interested in, run our Monte Carlo geometry processing, and we would get a reasonable results. In another example, we might be interested in a laminar flow against an obstacle like this turtle. So we invert the domain, we solve for the pressure projection in fluid dynamics. We see what happens there and invert it back. And we see this like laminar flow which extends from this infinite positive side to the positive negative side. So it's really able to pressure project given an infinite domain. But our method is not really limited to the Poisson problem. It can also be used with other PDEs, such as the Helmholtz problem, which is this problem of standing waves. And you can see that really our method is, to our knowledge, the first time that we're able to solve these sort of problems without using any artificial absorbing boundary layers or domain truncation. And really the method, the idea is still similar. You find a analytic function that captures the behavior as it's extending to infinity. For Helmholtz is this oscillatory behavior, and you solve for whatever is left. But it's interesting because we actually don't have support for solving Helmholtz PDEs using Monte Carlo geometry processing yet, so that's a very interesting path forward because Kelvin transform exists for solving it in the exterior problem, but in terms of solving it for the interior problems, we still need to figure out how to do it with Monte Carlo. Yeah, with that, that's all I have to say about using geometry for solving exterior problems. Thank you.
Hi, everyone. Oh, sorry. My name is Zilu. I'm currently a PhD student at UCSD. And today, I'll be given an introduction on my work on Euro Monte Carlo PDE solver. We're all excited about solving PDEs without the pain of discretization. And so far in this course, we've seen how Monte Carlo methods let us do this by using probabilistic interpretation like Wacom spheres to build unbiased sample-based estimators. But there are two common problems for Wacom spheres. The first is speed. We need to average from many independent samples to reduce the variance. The second is currently restricted to solve only linear PDEs. Over the last few years, neural methods such as neural operators and pins have emerged. Pins directly approximate a PDE solution by training a neural network to satisfy the equation and boundary condition. Neural operators instead learn a mapping from the problem parameters or forcing terms to the corresponding PDE solution. They're extremely fast at inference and can handle nonlinear equations. However, they're usually biased since it's impossible to enforce the training loss to zero. And seeing the complementary benefits of these methods, the natural question is, can we combine the Monte Carlo methods with neural networks to get fast, low-variance estimators that still preserve accuracies? And this question sits at the heart of today's talk. And as you'll see next, this trend of combining neural networks with traditional graphics methods is not new. In fact, rendering has already explored it in several forms. Neural denoisers, such as NVIDIA Optics, takes noisy path-trace images and clean them up in milliseconds, dramatically reduce the number of samples needed. And neural radiance caches uses neural networks as caches to learn and reuse the lighting, enable real-time global illumination. Neural control variates learn to approximate the integrand in Monte Carlo integration, using this prediction to reduce the variance while keep this result unbiased. In fact, these last two works directly inspired our own research. And other than rendering, in view synthesis, NeRF-style models enhance classical image-based rendering by filling in geometry and view-dependent effects from sparse inputs. Having looked at the hybrid methods across graphics, we now turn to our own proof of concepts. We focused on speed and did some initial exploration combining neural field with Wacom sphere solver. While Wacom sphere delivers unbiased solution, it faces two key bottlenecks that make it slow at inference. First, Wacom sphere needs high sample counts to reduce the variance. And second, for each sample, Wacom sphere might need long recursive walks before exiting the domain. To address the bottlenecks of long recursive walks, we propose a simple twist on the Wacom sphere solver that forms the basis of our neural caching project that was first introduced in SIGGRAPH Asia 2023. We propose that instead of continuing the random walk step after step, we pause after a fixed number of iterations and query a trained neural network to directly predict the PDE solution. And in order to train the neural field, we could use the supervision from Wacom sphere estimator and run a simple L2 loss as supervision. Turns out this noisy but unbiased estimator is in fact more stable than the self-supervised pin-style loss. And as you can see, when we changed the neural network architecture from Siren to Instant NGP on this 2D Poisson equation, Wacom sphere supervised loss produced good results for both network architectures, while the self-supervision loss caused catastrophic failures. And once trained, we plugged the neural field into the Wacom sphere loop for inference. Here, we compare the amount of time it takes for our method to solve a variable coefficient problem on this 3D bunny domain. And this yields up to 10 times speed up compared to the Wacom sphere method to reach the target accuracy. Here, we visualize an equal sample qualitative comparison. Compared to other methods, our method produces visibly cleaner results with lower error, confirming that the neural cache improves accuracy with the same computational budget. However, one limitation this method still has is that it still produces biased solutions, as indicated by the plot 2 on the figure of the right-hand side. This occurs because the neural field is a biased estimator for the integral. And now we're wondering, can we construct an unbiased estimator using neural network? And this question leads to our follow-up work on last year's SIGGRAPH, where we used the neural field as a control variance. The key idea is to rewrite the target function as a sum of two parts, one whose integral we already know analytically, and its residual term with low variance. And then we estimate only the residual part using Monte Carlo method. Inspired by AutoInt, we train a neural network to approximate the indefinite integral of the control variance function. We can then evaluate the network at boundary to get the integral and take derivative to obtain the integrand. Now we can build a neural control variance with automatic integration right inside our Monte Carlo solver. And because the integrand is recovered by automatic differentiation, the network defines both the function and its known integral, giving us a trainable control variance. We minimize the variance of the final estimator directly using a differentiable loss with standard optimizers. And we can see that while the network is being trained to match the target function, the variance of our Monte Carlo estimator steadily decreases. Once trained, we plug it into our Wacom sphere solver for a 3D Laplace equation. With the same sample budget, our method produces visibly cleaner and more accurate result. And again, here's the computational time breakdown chart. Including training overhead, our method requires the least amount of time to reach such accuracy, while other baseline cannot do that within the time range. And this makes our method ideal for settings that require high accuracy and high resolution. Note that the control variance method is a bit slower than our cache-only approach, but in return, we can get a fully unbiased estimator with significant lower sample variance. And to recap, we've shown two ways to integrate neural networks with Monte Carlo organically to build hybrid PDE solvers that are both fast and accurate. One is caching, where we stop the Wacom spheres early and query a trained neural field. The other is control variance, where a neural network learns the control variance function indefinite integral, enable faster solution while keeping the resulting estimator unbiased. Other than caching and control variance, neural networks opens the door to many new variance reduction strategies. For example, Huang et al. Recently proposed a neural-guided walk-on-stars approach for variance reduction, in which they learn a neural space condition guiding distribution to important sample high contribution regions. And next, we're still in the very early days of Neural Monte Carlo PDE solver. Right now, every model is trained from scratch for a single scene, tuned specifically to its geometry and its boundary conditions. One exciting future direction is to move forward to feed-forward Neural Monte Carlo solver, something that is trained across multiple geometry and many boundary conditions, so it can generalize without retraining. This will let us skip the costly per scene optimization step and move directly to fast inference for new setups. And so far, we've focused on how neural networks can help walk-on-sphere to improve efficiency. But we can also flip the perspective. Monte Carlo PDEs can also help neural methods too. In our early experiments, walk-on-spheres provide stable, well-founded training loss for HDD optimization. And that raises an interesting question. Can the strong theoretical guarantees from Monte Carlo methods help tackle nonlinear equations? By themselves, Monte Carlo methods cannot solve nonlinear equations, while neural networks can without the Monte Carlo guarantees. If we're able to bring them together, we could probably have the best of both worlds, a fast, provably accurate solver, or even help-guided smart network architecture design. And this two-way exchange, where neural help Monte Carlo and Monte Carlo help neural, opens up new exciting possibilities for the next generation of hybrid grid-free PDE solvers. And lastly, I want to thank all my amazing collaborators, and thank you all for listening. Happy to answer any question in the remaining chat.
OK, so thank you for sticking around. Now we're just sort of at the end of the course. And in this final section, I'll discuss some applications, limitations, and future work. OK, so to first summarize, today we've presented an emerging class of grid-free Monte Carlo methods based on the walk-on-spheres algorithm. These algorithms use random sampling to solve some pretty basic but pretty fundamental partial differential equations by framing them as integration problems. Walk-on-spheres inherits several advantages of Monte Carlo rendering, which gives it a unique place in the landscape of numerical solvers for PDEs. These advantages include trivial parallelization across many independent random walks, output-sensitive evaluation of the PDE solution, and scalability with increasing geometric complexity because of lightweight data structures. But Monte Carlo is not always the right tool for the job. I think one really has to take into account whether downstream applications can leverage the unique strengths of these random walk-based solvers. I'll now provide a very quick overview or sampling of some of the applications developed by computer graphics and computational physics researchers in recent years. We had actually invited some of these authors to present their work, but unfortunately, they weren't able to make it to SIGGRAPH this year. So you'll have to make do with me. So researchers at the University of Waterloo, McGill, and USC recently took on the very ambitious goal of solving highly nonlinear Navier-Stokes equations for fluid simulation using Monte Carlo. With either a vorticity or a velocity-based formulation, the key idea is to apply operator splitting to the Navier-Stokes equation, separately solving for diffusion or pressure projection using Monte Carlo, and advection through either a background grid or a neural network. Now, as I understand it, the motivation to use Monte Carlo was to avoid using conforming meshes or working with cut cell methods, which can be tedious to use with fine-scale geometry. But with a Monte Carlo approach, no special treatment is needed for handling such geometry. Now, these methods are very much a first attempt at using Monte Carlo for fluid simulation, and they're not yet competitive with state-of-the-art techniques such as APIC, FLIP, or lattice Boltzmann methods. But where I personally find a lot of potential in this work is that it actually opens the door to not just rendering, but also simulating only, say, the surface of the fluid through maybe a combination of ray tracing and a Monte Carlo PDE solver. I think we can gain a lot more efficiency by leveraging the output sensitivity of Monte Carlo. There's also some recent work on thermal imaging by researchers at CNRS, where the idea is to develop a unified framework for jointly simulating the coupled physics of thermal conduction and radiation through a combination of walk-on spheres and path tracing. At a high level, the authors first express these different modes of physics with respect to the same quantity, namely temperature. For each mode, they then write the temperature as an expectation of a random process. Finally, they generate a thermal image by coupling conduction and radiation at the interface between solid objects and air. The authors demonstrated that their method can also scale to larger scenes. So for instance, here's an infrared rendering of a neighborhood with thermal shadows using their StarDisk solver. Now, switching focus from simulation to geometry processing, researchers at Pixar last year presented a hybrid walk-on spheres and finite element approach to compute barycentric coordinates for character deformation using control gauges. The authors had two primary motivations. The first was to be able to use different types of cage geometries, for instance, messy polygon soups, control splines, or a mix of the two. And the second motivation was to bypass discretization artifacts from coarse volumetric cage meshes, as the Monte Carlo approach, shown here on the right, allows you to instead directly compute barycentric coordinates at arbitrary query points inside the cage. A nice innovation of this paper was to show how to denoise Monte Carlo estimates using Gaussian filtering or Laplacian smoothing, and to also guarantee linear precision of these barycentric coordinates by applying weighted least squares on the Monte Carlo samples. At SIGGRAPH this year, researchers from NVIDIA will present an inverse rendering algorithm where the goal isn't to generate an image given the geometry, materials, lights, etc., but rather to recover these scene parameters from either a dense or sparse set of images. Now, a key challenge with getting inverse rendering to work with a Monte Carlo ray tracer is to accurately sample visibility silhouettes, without which optimization can fail to converge. But sampling these silhouettes is a really hard problem. So the authors instead propose to reparameterize the problem. At each ray bounce, they now solve for a velocity field in the vicinity of the silhouettes, which satisfies a Laplace equation. This algorithm is actually the first example that I know of where a path tracer uses walk-on spheres as a subroutine. Also, because of the high dimensionality of this problem, it's actually completely infeasible to use a grid-based alternative. The end result is unbiased gradients for inverse rendering, which makes optimization more robust compared to previous methods. In the same session, Bailey will present a walk-on spheres algorithm to solve differential equations in participating media, such as clouds, espresso grounds, or extracellular fluids. These media are defined as a collection of microscopic particles, like water droplets in a cloud or ions in a solution around a cell. And unlike scenes with only boundary geometry, these particle collections can actually be really challenging to work with because in many cases, we don't even have an explicit geometric model for them. It's just a probabilistic description of their distribution. This paper successfully extends walk-on spheres to handle such particle collections, making it possible, for instance, to accurately compute electrostatic potentials around complex cellular membranes in ionized fluids. Independent developers have also come up with some creative use cases for walk-on spheres, such as agent path planning. So in this demo, the ball follows the character around the scene by solving for a harmonic vector field that points in the direction of the character. This vector field is computed locally on the fly, only at the center of the ball. Finally, as Shuang discussed in his presentation, researchers are now developing differentiable solvers for PDE constraint shape optimization, where the goal is to recover the shape of an object given measurements like temperature or electric potential. I believe these types of solvers can eventually open the door to many real-world applications, such as electrical impedance tomography and the thermal-aware design of circuit boards. OK, so I hope these applications give you some sense of how people are using Monte Carlo solvers today. But a question that we keep getting, and it's very difficult to shake off this question, is at the end of the day, how well do these Monte Carlo algorithms actually work and compare against traditional solvers? So my honest answer is that there really isn't much value in making an abstract apples-to-apples comparison between different solvers. Each framework has complementary strengths that can augment your workflow in different ways, and the choice of solver ultimately depends on the requirement of your application. So for instance, when meshing is not a bottleneck, then finite element methods may be a great option if accuracy is paramount. Monte Carlo solvers take more time to converge, but they can be more robust and offer new opportunities for iterative design by making simulation more like rendering in terms of progressive and output-sensitive feedback. And finally, physics-informed neural networks can be used, are desirable in scenarios like climate modeling, where we have a lot of sensor data, and where we want to model highly non-linear turbulent flows, for instance, on the spherical geometry of the Earth. But unlike Monte Carlo and FEM, the weakness of these solvers is that they currently have to be specialized or overfit to some particular type of geometry, boundary conditions, or some other PDE input. So really, in my opinion, each solver has its own place, and they aren't quite perfect replacements for each other. I think it's also worth pointing out that there wasn't always consensus around the place of Monte Carlo methods in light transport. If we travel back in time and read emails from the 90s, we see that there was a lot of skepticism and doubt about whether Monte Carlo methods were worth pursuing in rendering. So for instance, one person on this thread comments that, I can't see any advantages of these methods except that maybe meshing is not needed. And so broadly, there was a concern that Monte Carlo methods were an academic curiosity, but one response from Pete Shirley stands out. He said that Monte Carlo is so dumb that it actually doesn't get hit by any big scenes, and he adds that it's really easy to implement. So this simplicity of Monte Carlo methods is not just a convenience when it comes to implementation, but it's also in line with the famous bitter lesson from Rich Sutton, which says that we should try to develop methods that scale with computation, even as computation becomes very great. OK, so what's next? I think we should continue working towards extending Monte Carlo methods to solve more complex physical systems. A challenge that we've run into, for instance, with the Helmholtz equation, is that the operator norm of the mean value integral for such equations is greater than 1, which naively suggests that an estimator is not convergent. But maybe there's some interesting or clever geometric insight or preconditioning one could apply to get around this issue. So if you figure it out, please let me know. Going from research to production, we need efficient GPU implementations of these algorithms, as well as, I think, a PBRT-like framework with demo scenes of varying complexity that makes it easier for the community to experiment with these algorithms. We are finally going to open source version 1 of such a framework by the end of August or early September. So please stay tuned, and thank you for your patience on this front. Monte Carlo solvers are still fairly young, and more effort is definitely needed to reduce noise and improve sampling efficiency, potentially through AI-based neural denoisers, as Zilu mentioned earlier. I genuinely believe that it's still possible to improve efficiency by a few orders of magnitude from here on. I think there's a lot of money left on the table because of the spatial smoothness of these underlying PDEs. And finally, we should remain on the lookout for applications where the unique capabilities of Monte Carlo methods really shine. Now, there are a lot of resources available online if you found this course interesting and if you want to dive in further. We maintain a web page with a list of publications, tutorials, and code snippets, and slides for this course, as well as the one weekend series will be made available here later this week. If you don't want to read multiple publications and prefer reading a single document, you can check out my PhD thesis. More broadly, PBRT is a classic resource for learning about Monte Carlo methods applied to rendering. Keenan's CMU course on Monte Carlo methods and their applications is also a really nice resource. And finally, for a deeper dive into Brownian motion and its connections to PDEs, I recommend Brent Oxendaal's book on stochastic differential equations. And that's it. Thank you for listening, for sticking around, and we'll open the floor to questions.